without affecting the waters. This is the basic block diagram for the underwater ROV, where we have used buoyancy and feather wires. This is the sample ROV we have designed.
Hello, myself Sharad Mane. Coming to the methodology. Step one was required analysis. As this was the first underwater project, we had to do thorough literature survey. We uh, we took on hard literature survey. We read most of the research papers and preferred online videos. And according to that, we decided the material and the components used. We decided to use PVC pipes for sturdy and lightweight material for our underwater project. Next, we used Next, we used 1200 RPM motors, gear motors, and endoscope camera with 6 inbuilt LEDs for underwater inspection, which can also be used in dark places where the light can't go in deep sea. Next, no, and next thing was system design. As we said, we preferred various literature survey papers as well as online videos. We created a CAD design according to that. Also, we had to adapt to our designing based on our literature, based on our outcome. Component integration. We used the SRM fabrication lab and various cutting and fabrication tools to build our project. Testing and evaluation. We integrated various components and tested individually and as a set on a localized water body. Final implication was real world test where we have tested the definition of the camera and the inspection material outcomes. According to the test carried out, we did below are the research findings: stability, buoyancy, camera system, control system, power efficiency, structure design, waterproof electronics, as well as signal interfaces. All were on the optimum level. Our project is far from perfect. This was the founding stone for the great research in underwater inspection. So there are many areas for improvement. Like we can add VLDC motor instead of DC motor. Also, we have decided to integrate various sensors like temperature, humidity, as well as flow sensors to increase the efficiency of the rover. Alongside with it, the main area of focus was to add AI and adaptive control to improve the maneuverability of the rover. Also, we are planning to add a underwater robot manipulator arm. So instead of just inspecting the underwater system, it can also manipulate it. These are the key references from all the research literature review you have taken. Thank you. Yeah. So, is there any questions? You have completed this integration? Yes, sir. Any photos? We have posted in papers. What about the test results? Test results are we carried out different things. We have sealed the motor using glue, adhesive glue, and we have tested it underwater. And also we have put the motor in underwater, but it went till some depth. It was hard, but yes, it went till some depth, and camera was working also fine. Underwater camera. Okay, thank you. Hi. Thanks for the presentation. What is the depth for which your motors are sealed with the glue that you are using? What kind of a time rating are you targeting? We have used the connection. Instead of wireless connections, we went for connection wires up to 10 to 15 meters. The We have tried for 15 meters, but the wire resistance was increasing, and the three different batteries we have used 12 volt batteries for powering each of the three 1200 RPM motors. So to maintain the minimum resistance per depth ratio, we decided to keep the depth at 5 meters. Also, the endoscope camera we have used also has the wire connection of 5 meters.
Okay. I have connected the endoscopic camera with the phone. We can display the image by using the phone. Such systems that we have tested so far of the just the legs you know nearby. Then it gives the good results according to the camera inspections, and it is very stable in underwater. Okay. My last question is, you are using PVC. Do you think there are any material disadvantages to the environment if PVC is submerged in water for longer times?
Yeah, actually we have searched long time. There are many good materials instead of PVC, but our main focus was to create a cost-effective material rover. As this was our subject project, we didn't have lot of the funding, so we were trying to maintain the overall cost of the project less than 5,000. So PVC was the cost-effective as the study material. Our main focus was to create a base foundation for the future studies. So only for underwater deep dive and camera inspections. That is only our main focus for now.
Okay. Thank you. Thanks.
Thank you so much for your presentation. Author of paper ID 73, you may now take the stage. Paper ID 73. Hi everyone, my name is Arya and I am working as a JRF under Dr. Jairam Vallaru in Chemical Engineering Department at IIT Ropar in Punjab. So my topic today is how to detect marine heat waves using machine learning models. So before we jump into marine heat waves, let's see what is sea surface temperature or SST. From the name itself, we know that it is the temperature at the surface of the ocean, and it is a very important ocean variable which affects marine ecosystem and climate. So, if we are able to predict SST early, it will be beneficial for ocean advisory systems and marine heat wave detection. So, marine heat waves, it is a unusual rise in SST above a threshold value in oceans. So this unusual rise in SST leads to extinction of certain marine organisms, and also it will affect badly for fisheries. So for marine heat wave detection, early prediction of SST is beneficial. Usual or conventional methods for SST prediction is physics-based models, but they are time consuming and expensive. Capture all the complexities in ocean environment. So what if we shift to data-driven models, because we have huge amount of historical data available. So uh, data-driven models can be statistical models, machine learning models, and deep learning models. So here specifically we are choosing LSTM, long short-term memory neural network. So before we jump into marine recurrent neural network, and it can handle long-term dependencies in time series data. Our SST dataset is a time series data. So the main objective of this study is to predict SST using deep learning models and to increase the lead time of this prediction and to detect marine heat waves from this predicted SST. So before we jump into the methodology, we will see the formal definition of marine heat wave. So the first term related to this is climatology. Climatology is kind of like an average of SST calculated over some baseline period of 30 years. And threshold is the 90th percentile of this SST data over a day calculated similarly over a period of 30 years. So this threshold data is kind of like an upper limit. If the SST rises beyond this threshold continuously for 5 or more days, it is considered as a marine heat wave event. And the next topic is LSTM. And we have this is a long short-term memory neural network. It will handle time series data, and there are two cell state and hidden state. Hidden state is kind of like a short-term memory, and cell state acts kind of like a long-term memory. And there are 8 mechanisms inside a single unit of LSTM cell, which controls the information flow. Forget gate will remove unwanted information from the cell state, and input gate will add relevant information to the cell state, and output gate calculate the output of single LSTM unit. The next model is MISO NARX model. MISO is multiple input, single output, and NARX is a non-linear autoregressive model. Autoregressive, from the name itself, it means that in order to predict future values, we are using past values as input. So our proposed model is a MISO NARX LSTM model. So in order to predict the SST at the time t, we are using the SST from the time step t minus 6 to t minus 15 as input, and some other additional variables. So here we are leaving a window of 5 days. That is the SST value from time t minus 1 to t minus 5, because we are going to predict this SST 5 day early. These are the results. So we have chosen a location in Bay of Bengal. Um, and in this graph, the green line represents the climatology, that is seasonal average, and black line represents threshold, and red line is the SST satellite measurements. So from the graph, we can see that in November 2019 and August 2020, this satellite SST measurements are going beyond this threshold. So two major sets of marine heat wave events are happening. And the blue line represents this meso and ARX LSTM predictions. In the same time period, these are also going beyond the threshold. We are not able to capture intensity, but at least we are able to use some quantities. So out of two major events, we are able to capture two, and the R2 score of this model is 0.68. To
So
conclude,
we can get
now we move forward to the question and answer session.
We have given underwater visual images.
Okay, to
ROV.
conclude,
like rapid chemical transformation of ocean water is happening due to CO2 emissions. That's why we are trying to do a research on this to bring light into this factor. So rising CO2 leads to falling ocean pH. And finally, it will disrupt the marine biodiversity, food chain, and economies which are dependent on ocean resources. So we are trying to integrate the explainable AI. So traditional methods are they lack the ability to clarify the complex interdependencies. So we are bringing explainable AI and also multi-resolution random forest and LSTM to help the analyze of long-term acidification from 1950 to 2100. So these tools provide transparency and which are essential for policy decision making. So first we will integrate the data modeling thing like historical data which will be fused with like microeconomic and the other environmental indicators. Then we predict the tipping point of the ocean acidification and the main drivers, like the factors which are driving this acidification. And also, based on this, the policymakers can make the policies to reduce the ocean this pH, like control the reduction of pH, and finally the ocean will be a better place so that marine ecosystem can survive. As you can see, these are our literature survey. Like few work has been done in ML climate sciences and all the factors, but no one has gone into the depth and they showed which um, these factors are working in, like contributing to how much this thing. So for better and using better AI technologies, we are trying to do our. So as you can see, like this is the problem statement, like ocean acidification, like which is because of the rising emission of CO2, which is finally disrupting the marine ecosystem. So traditional methods are failing. So that's why we have use this explainable AI so that there is a
Got
clarity
and I want
we
attention all
use
students.
for making the policies. So objectives of our work are the analyzing long-term trends and then identifying the key drivers like the CO2 emission, temperature rise,
using random forest feature importance and also predicting future ocean pH levels and also using the LSTM techniques. And we are also integrating the explainable AI to provide transparent and interpretable insights. And finally, this will help the policymakers. So it will lead to climate intervention and the minute. So as you can see, this is the our block diagram. First, we are collecting the data, then we are going to three stages of pre-processing, and then the dual model pipeline is the random forest and the LSTM. So random forest is calculating the feature importance, and LSTM is producing the future projection. And after that, we are using the explainable AI, which will finally give the actionable this environmental intelligence. So like using these like prior studies and statistical model to predict so we have a better result than the previous works which have been done. So this is the steps as you can see like pre-processing then random forest like which is showing the CO2 emissions as the dominant factor like which is we have 41% of the total, all the factors which is contributing to these things. And also, our LSTM model shows that the ocean pH trend will reach a tipping point by 2075. And also, we have received a high accuracy, and also our R square score is 0.9. Like R square is this it is a matrix which shows how well this regression model works, showing the variability of the target factor. And also, Lime and shell has been used for providing the instance level prediction and the overall picture of the like trends which are happening. Finally, this will like give our results. Now I am passing over to my co-author Mushit for the rest of the presentation.
Good afternoon, panel members. So we're moving toward the research features, that is a random forest plus SAP. So basically, what is this doing? This is having a CO2 emission, which is showing the top contribution of the factors in the acidification. Basically, how does this happening in the water of the oceans? Basically, your carbon dioxide plus your water is contributing to a carbonic acid. So that is the main factor which is enabling this thing. Then we have multiple features. What is tipping point, which I will basically confine to that? Basically, your environment touching a certain changes which is irreversible after that point of certainty. So basically, 2075 will be the time. If we continue with these or factors, for sure we are not gonna recover that back. It will be irreversible. These are the major factors. Now, Lime shows the sudden drop in pH values. There was a 5.3% of pH value drop, means moving from the basic or alkaline to acidic part. There was like 8.8 to 7.7. There was 5.35% of drop. Next slide. So this was basically the showing of the graphs, multiple features over there, especially for fossil fuels. Then LSTM showing the actual and the predicted values, and then you have the future ocean pH value graph. Next slide. So this is the conclusion which I explained to you. Basically, yes, future. I will go to the future scope next. This will be 5.3% increase in the ocean acidification over there, and the tipping point I told you, the climatic policies and the government monitoring systems, environmental monitoring systems were there. Now coming to the future scope, how can this research contribute basically to the our sector of domain? So one was that policy making, local policy making. Basically, if we find that in some areas there is ocean, the pH value is dropping, going to the acidification, which will harm the ocean life and ocean basically aquatic animals and your plants. So there can be local policy can be made there. Conservation programs can be made there. Then we have marine biodiversity loss and economic loss. We can contribute and make a touch to that point.
To the question and answer session.
Thank you for the presentation. What are the different data sets that you have used in order to create your AI model? Actually, from 1850 to 2022, we had collected the historical data. Like it was given in one of the this UNEP, like United Nations Environmental Program. They had a data set, public domain. Yes, and for that, and also like IPCC also had this. So we combined both the data set and made the all the 17 columns which are required, and also like one NGO's data set was there, which was in open source, which was had given the approximate projections of that. So, but we are not sure whether the projection will be correct. That's why we had used our LSTM to train on the historical data and match whether these projected values and how our projection has got. So for the future things, we are comparing with the past thing and like being able to predict how much this ocean pH value will decrease. That was the
Okay. There are a lot of species inside oceans still which are unexplored, and those are those who are explored live for around 50 years, 60 years, 100 years inside the ocean. So, do you think with the increase of acidification, with the kind of percentage that we are having, these species are making up for this change in any way, or they are adapting to this change? And
like
what, if at all not, what is the overall impact on the marine life?
actually really because of ocean acidification and this like especially the areas of ocean where high temperature, many species are moving to colder places, like those who are adapted to cold water. So their habitat places are getting changed. So, and what few species are there surviving warm water, so it is good for them. But most of the many species are adapted to cold water, so it will negatively impact them because day by day, suppose they are moving from area A to B, then area B will also become hot one day. So how much they will do, so that will ultimately lead to fate of lot of species and maybe lead to extinction also because already we are seeing some species become rare there. The government is making laws to protect them.
Good of, again, the question is on the increase in the acidity level. From 150 years, that is from 1950 to 1400, is at 5.3. What is the permissible value? Anything else mentioned? So this 5.3 increase, percentage increase in the ocean acidity. I understand it is from 1950 to 4100, 150 years. Is there any permissible level been mentioned? Like it should be only within 6% or 2%, something like that.
No, like not any limit, like we are calculating how much drop it is happening. Like
So sir is asking, how is 5.3 a big percentage? Is there the maximum limit to which it shouldn't cross that?
actually, I think in Kyoto Protocol or Paris Climate Agreement, I don't exactly remember the name of the conference well, but they had made one target to hit less than 1%. That was the target. We have already crossed. So that is quite harmful. Like even 1% is also harmful, but like that was the main target. First 1%, then they had planned to reduce it. So that way we have already crossed that. So it is really harmful for the millennials.
At least then, can you give a figure from 1950 to till that is to 2025? What is the increase? And from 2025 to 2100, what will be the increase? There any figure like this?
Sir, like we have calculated, like Bangkok, sir, out of 5.3 already more than 3 something with 3 point something has been done till now. So rest like that.
That means, shall I conclude that previous 75 years we had a higher increase and now the coming years will be having less? Shall we
Yes,
conclude?
because now you know
you so much for your presentation. Now, author of paper ID 185, please proceed to present.
That means, shall I conclude that previous 75 years we had a higher increase and now the coming years will be having less? Shall we conclude? Because now
so much for your presentation. Now, author of paper ID 185, please proceed to present. Invite the author of the paper ID 177 to come forward. Paper ID 177.
Start before something is on the screen, just to not lose much time. So the talk which I'm going to give is about the marriage, about marrying two different objects in nature. It is marriage between physical and biological processes in the ocean. And I want to show how it happens if we use artificial intelligence and whether there is a good baby which can be born from this couple. Uh, now it is. Uh,
Invite the author
can I
of
operate it?
177 to come forward. Paper ID
Okay.
177.
So it is like that. We all know that the physical processes are very important about for biogeochemistry in the ocean today. However, biogeochemistry has its own life, and it is not by default clear how strong this dependency is, and whether we can much use physics in order to forecast biogeochemistry. There are some problems also with the data. There is model driven forecasting, there is data driven forecasting, and there is some hybrid between each, which I'll be talking about. Why I start my talk with it? Because we have several platforms which we use in oceanography just to learn about the ocean, to investigate the processes. One platform is satellite. Satellite altimetry has brought huge progress in oceanography because it measures very accurately sea surface. Sea surface gives you an idea about the barotropic pressure gradient, which is the driving force for the ocean. But it is not enough. Barotropic pressure gradient measures what is on the surface and it does not see what is in the deep ocean. After some time, there were robots, cargo floats, which have been developed, which started to measure profiles. Now the ocean is seeded with cargo floats, which gives us three-dimensional structure of temperature and salinity combined with sea surface from satellite. It ensures very accurate estimate of the dynamics of the sea. That is about the physics. The problem is that we cannot say exactly this about the biology because first, we don't have enough sensors, and second, because the seeding with biological sensors is not so good like with physics. Biological sensors are much more important. So all these sensors, biology, most of them actually use optical methods in order to measure oxygen, to measure chlorophyll, which is let's say plankton, to measure backscatter radiation, which gives us particles in the ocean, even small micron big particles. And what these devices also measure is light. So the question is, can we bring these measurements from biological flows together with physical data from models in order to make a step toward constructing 4D view of biogeochemistry? So this is actually the aim of our work. So
application is for the small sea called Black Sea, which is the easternmost sea of Europe. It is enclosed sea with very limited exchange with the rest of the ocean. And because of the high river runoff and the limited exchange, we have conditions for creating anoxia. So you see on the picture on the right below the distribution of oxygen, which is down to about 200 meters below. This here is anoxic. And there is a strong maximum of nitrates, which gives a life in the ocean. And my talk will be about the layer between the surface and about 100 meters, which is the so-called photic layer. So the question is whether we can analyze from BGC measurements important correlations or dependencies between different biological parameters and their dependence on the physical parameters. So what I said at the beginning is shown in this picture. We will be using biogeochemistry, Argo data, and this is the data which we use in the paper I'm presenting. It is about 6,000 profiles regularly distributed over the entire sea surface. We have physical data which are based on very well-established numerical models, operational models which are used for ocean predictions. And this is Siemens physics, which we want to combine with PGC observations in order to get for the description of biogeochemistry in the Black Sea. So, just to give you an expression of what data we use. So these are again show the positions of the float. What you see below is temperature profiles over several years, salinity profiles, so you have very strong stratification, seasonal thermocline in summer, radiation is reduced very strongly in the turbid waters. This is a very important source of life. These are the nitrates. So here you see how oxygen, it correlates very nicely with temperature, and it is very well known why. These are the particles, the small particles which are associated with coccolithophores, but also with bacteria in the Black Sea. And this is the chlorophyll, which you can think of as plankton. So now we have several plots like that. We want to combine them with the physics and see whether we can get realistic forecasts or estimates. Excuse me. Of the state of the Black Sea. We have also, as I showed, data from physical modeling as well as data from BGC modeling. BGC is biogeochemistry modeling in the Black Sea using a very complex model. This is also operational model. And for this bringing together physics and biology, we use feed-forward backpropagation neural network. It is the simplest most network because the data are very limited. We have not huge data in order to implement fancier approaches, although we recently tried this. So we have validation and training data set with the floats which are available. And let me now show to you some kind of challenges. The big challenge is that the only good correlation is between nitrates and density. So this is the clear with big numbers correlation values, and all these correlation between different fields are very low. So many scientists have tried to find different relationships to easily explain the dependence of biology on the physics, and it didn't work. So we decided to invite, so to say, the neural networks to see whether they can do something smarter what scientists could not do before. I'm sorry, it cannot change. Can you help? Okay. So what you see is that we have on this graph oxygen, DVP, backscatter, and chlorophyll on the left, and then you have the emulated parameters. You see that more or less bringing physics, biology. So we use physics from Argo to force to train a system which computes. So we have as a target biology, and we develop a model which, based on physics, emulates the biology. And as you see, it is quite successful, as in the Hofmiller diagrams as well as in the graphs, which gives you the integrated over the upper 70-meter layer concentrations. And the indexes of agreement are rather good. Can you change the slide, because I cannot from here? So we did actually the next step, challenging our model to ask the question, okay, whether we can just kind of substitute what is provided by biological model, which is not so good. I will show you this, by using input from physics of operational models, so to say, to marry physics from operational models. So this is 4D physics with the biology which is measured by Argo flows. So what we did were several experiments. In this first column, you see we show the for floats. So for 1 year, this is a testing year, a vertical concentration of chlorophyll. And what you see is that, so this is actually what we do if we use physics from Argo. We decided just to subsample the physics in order to get the coarse resolution which is appropriate, which is the one which the models have. And we used Argo data physics with the vertical resolution of numerical model, and we see that again the comparison between the first and second column are quite reasonable. Then this gave us the courage to say, okay, let us replace Argo physics with model physics, and this is the result. So you see that if we instead Argo physics use the model physics, then we get very reasonable results. And if you want to know what this is actually what the operational biological model for the Black Sea is giving. So it is very wrong actually, but we cannot do it much better. Nowadays biological models are not so good. So therefore, this was a very good step ahead just to use this training which we did with Argo floats in order to create biology based only by physics. Can you change the slide, please? So we did actually some further tests to see the comparisons for the entire system of floats, and this is one example here for one of the floats. So this is the data from Siemens. This is the operational model. It does not have backscatter, so it has also only oxygen and chlorophyll, and you see that chlorophyll is very, very bad. But this is the reconstruction using Siemens data, using physics with a model, and these are also reconstructions based on Argo. So you see that this panel here, these three pictures are very similar to this one. So to say, we very successfully, by bringing together physics from numerical models and biology from Argo, can construct the 4D physics patterns of biology in the Black Sea. Can you please change the slide? So this is one illustration. The question is whether from this patchy data, from this local data, we can extend them over the large area. And this is what you see on the left. On the left-hand side, you have annual mean concentrations of oxygen, DBP, which is backscatter, and chlorophyll. And we compare them with observation. It seems rather very reasonable. And what we see on the right-hand side is that the model also allows to reconstruct the for the eddy structure of the Gaussian chemistry. It is also possible, please next slide, to reconstruct the temporal evolution, and this is actually appears a very powerful tool if we want to make some forecasting for the BGC in the sea based on this combination of these two data sets. So now allow me at the end, please next slide, to draw some conclusions. First is that with the help of machine learning, we can address the issue of undersampling. This issue will stay for a long time. We will never have enough sampling, but with this nice combination which we did, it is possible to avoid this problem. It is possible also to enhance the quality of BGC numerical simulation by using products like what we do for data simulation. We cannot produce products for everything, but what we produce is 4D. Actually, it is very useful if you want to simulate data in the logical models. This approach gives you a possibility to better understand the functional relationship between different biological parameters in the 4D space, and it is also possible to get a new view on the eddy structure, on eddy processes in the seas, which has not in the deep sea, which has not been known except from some glider observations, but for very limited areas. So what we learned is actually, and this is the beauty of neural networks, is that the level of input and output are not proportional. This is not a linear system. So perhaps small changes in input can, in some cases, result in large outputs, large outputs in the system, and vice versa. And this was very hopefully done by neural network, and this kind of supplemented the try of different sciences before to find some functional relationship between different variables. So I think that transferable issue is also something which deserves attention, because this approach can be perhaps used for other ocean areas, and we recommend people to follow this pathway. Thank you.
Good afternoon, sir. Thank you for the presentation. I have a small and a quick question. Uh, could you please highlight the performance accuracy of this model as far as salinity, temperature, and chlorophyll, these three parameters are concerned, apart from oxygen?
I give some estimate index, give you some estimates of the index of agreement, which is red, given in red, and the definition of this index is given with black. So the best performance we have for oxygen. Oxygen is much is easier parameter to forecast, because oxygen very well correlates with temperature, and it is much more difficult for the plankton. And you can see on the bottom plot that also plankton, also although it follows the curve of the observation, it is very noisy. You see, from this noisy picture, you cannot get much similar result. The model smooths it a little bit, but nevertheless, 0.81 is not so bad.
So one last question I have. What is the data format that is obtained from the flow, and how difficult it is to integrate it with the numerical data and management thing?
So actually, in Europe, there is this Copernicus marine system of forecasting, which consists of two blocks. One is data, and we have different boxes for data. we have data for surface temperature, for ice, for for waves, as well as Argo data. Argo data are brought to Siemens. They are part of that. And their formats are very easy to use because they are uniform with the formats of the rest of the data. And in the other block, you have the modeling. So this modeling uses also this data from the first block, temperatures, etc. Everything is being assimilated because these models are run in assimilative mode, but not for biology.
Thank you so very much. Thank you.
Thank you, sir, for presenting. Now the paper ID of 185 authors can please proceed to present.
Some estimates of the index of agreement, which is red, given in red, and the definition of this index is given with black. So the best performance we have to, for oxygen. Oxygen is much is easier parameter to forecast because oxygen very well correlates with temperature, and it is much more difficult for the plankton, and you can see on the bottom.
Okay, while it goes to the first slide, hello everybody. My name is Joshua, and so today I'd just like to talk about our research work. And just a side note, like I realized that most of these papers in my lineup are all sorry.
You cannot get much much similar result. The model smooths it a little bit, but nevertheless, 081 is not so.
So, anyways, I just wanted to give a side note that uh, every other paper in the lineup was on oceans, but this is on farming. So I apologize if I sound like a fish out of water. But I just want to start by saying that our research is focused on smart farming practices in just generally. The thing is, we see a lot of research, we see a lot of articles about smart farming, but then I started realizing I couldn't see it in my next door neighbor farm or like the next door farm. And then I realized like there was a very small adoption rate when it came to implementing smart farming technologies into regular farms, like in for the people who actually need it. So this research work tried to focus on developing a model um, that could be integrated into smart farms, into regular farms. The reason the adoption rate is so low, it's almost 10 to 17%, is because of three factors that we were able to gather. So the first being costs, the second being complexity, and inadequate localized insights, which I'll explain in a bit. So the whole idea is that a lot of, excuse me, you can go to the next slide, please. Okay, so the objective of our work is to basically develop a low cost framework that can be implemented in any farm. Like the people, because there are almost, if you take 150 million farms in India, there are 135 million farms that do not have smart farming. So we need to have a low cost framework that's scalable. And we need to introduce the idea of multimodality, which is basically integrating different formats of data to to localize or to basically procure like specific intelligence, because it can we go to the next slide please. So the whole idea is that farms have general intelligence with the current establishment. So I'm trying to work on a multimodal approach for developing localized insights. I'm having a hard time. Can we go to the next slide, please? Okay, so basically, the proposed methodology is a framework, and the entire idea is to converge different formats of data and to basically garner insights that are specific to each and every farmland. So the idea is next slide, please. Okay, so basically, the idea is what is the most accessible form of data that you can collect for someone, say, who doesn't even have a digital literate background, like a farmer. A smartphone itself has a camera. It has the ability to store observations or record of observations. It also has the ability to, it also has a GPS, which is surprisingly very efficient uh, and enables you to collect a lot of different sources of data. So if you look at the block diagram, we I try to bring in different types of different formats of data, and we had a data fusion module, which all of the different formats of data go into, and then we run it through a bunch of different machine learning models, which then give us an insight into. Next slide, please. Okay, so when I say, I'll just quickly talk about the different formats of data. So, for example, number one, phenological data, which is a record of observation. So, a farmer could log in when he's sowing, when he's harvesting, when the root is established, when the leaf is established. All of that is phenological observations, which a smartphone can handle. The next is soil data, like pH levels, the acidity level, and things like that, which are available through sensors, and there are other ways of obtaining that as well. But most importantly, satellite data. Satellite, surprisingly, yeah, it's okay. I'll just continue talking. Surprisingly, satellite data is we're able to extract a lot of information through satellite data, and we realize that there are a lot of satellites up there which provide us with different formats of data. So, can we just move to the next few slides, please? Okay, can we go back? Go back. Go back. Okay, so what we did was, I use an image for getting the image of the soil. So what we did was we compared a soil image classification model, and then we also compared it with a multimodal approach. So mixing or like merging or fusing soil with an image with data such as that is available through sensors like the acidity level. And we saw next slide, please. We saw there is a difference in the accuracy. So we were able to get a much better prediction, or we were able to get a much better insight when we're using a multimodal approach. Next slide, please. We also worked on a harvest model. So, sorry, a prediction model that basically was able to provide us with a lot of predictions. Can we just skip to the end? So just the previous. So we were able to use that mathematical model to basically merge all these different types of data. You can just keep going. You can keep going through. So this is just a sample of the data. This is what you can obtain from next. You can just keep going. This is what you can obtain from the satellites. This is an example of all the data sets. Keep going. That's fine. Just keep going. Just keep moving. Yeah, that's fine. So this is an example of what you can obtain from just coordinates from a coordinate system using NDVI filters. So we can use for vegetation. Just keep going. So the idea is, just go to this conclusion. The idea is that we were meant to develop a low cost, accessible framework that can be practically implemented in farmland. So that's the whole idea. And I know I'm sorry about the presentation because I couldn't cover a lot of things, but I'm happy to answer questions. Good afternoon. Very good presentation. So, first question is the low cost. Yes. How you are claiming that it is a low cost model? Okay, so it's a low cost framework. The whole idea is, if you look at smart farms that are implemented right now, the infrastructure costs are huge and it's only found in urban areas. But if you look at smallholder farms, the rural areas, they don't have that infrastructure to build like irrigation systems or sensors and things like that. So my idea was like, how can we get smart farming and AI technologies into the hands of a regular farmer? And the idea was like, you see a smartphone, like every farmer has a smartphone, they have it right now. So what is the most data you can bring in or collect using just a smartphone? So that was the initial thought process. So even with the smartphone, you can just like I said, we have data collection sources, images, for example, which can run a soil classification model. GPS systems, which is able to provide us with satellite data. So we are able to collect NDVI. I couldn't run through everything, but with GPS, we were able to use tools to calculate the boundaries of lands like parcels. We're able to calculate weather patterns. We're able to calculate the vegetation index for the past 10 years. So that way, you're getting a specific understanding or insight into a specific piece of land. That is the idea behind the low cost. So we don't really have a cost involved when we try to implement the framework. I hope that makes sense.
So, next question is that there are so many data vision models that already exist. Yes. Then what is the need for this proposed method and how it is having advantage?
Okay, so there are a lot of data fusion models. Again, they're expensive. They need like a lot of different frameworks to even manage them. Like, for example, they would need like heavy computational power. So my idea was to find a very low complexity solution and that takes very low computational resources. So it's a cloud-based service, of course, but we're trying to make it as efficient as possible and as low computationally resourceful as possible. Okay, thank you.
Thank you so much for presenting. We invite the authors of the paper ID 189 to come forward. And my colleague Punateja is here. We are from RMK Engineering College. And the topic is about the Wi-Fi powered underwater data and audio transmission. And it's a type of communication system with transmit data and audio. So coming to the introduction slide, I'd like to explain the uh, before model which we are using at our communication system. So actually now we are using the sonar, right? Sound navigation and ranging systems that transmits sound waves and receives the echoes, like transmit signals and receives and the type of echoes. And coming to the proposed model as we before. So coming to the main objective, uh, we discovered the light fidelity technology. Here we use LED to transmit the data and audio from transmitter to receiver side. And coming to this project, we use different modules here. Coming to data and audio, there is a different types of modules we have used from transmitter and receiver side. Next. So coming to this problem statement, you will explain.
So here the problem statement is before we are using the sonar technology for the transmitting data and communication for the transmitter to receiver. Now here the main impact of our project is that we are implementing using laser and LED for the transmitting the data and audio to the receiver. So here we can see that achieve and faster and more relatable data transmission with no distractions. Either we can see in the sonar there will be some distractions in the marine life, but compared to using L5 and the LED as well as using laser, there may be no distractions during the during passing the audio and data.
So actually we done a small prototype on this project. Here is the block diagram representation which we have done recently. And this is a transmitter and receiver block. We use Arduino Nano for both sides, small prototype for that. And we successfully got the output from this side. So here we use two different modules for transmitting data and audio. And as well as the receiver side, we use two different receiver modules, solar panel and photodiode. And there is an audio amplifier which amplifies the sound which we get from a transmitter side to and receiver side. Um, so there is a I2C module which displays the data and LCD. So which is a proposed methodology was integrating the so reducing these modules from transmitter and receiver. We can make a receiver module in a single piece. So coming to the light fidelity, also we can use LED laser, laser which we can use for higher wavelength and LED for short range communication and effective transmission data rates. Uh, and coming to sonar, sonar also you know that it affects the partial this aquatic system, like whales, these also produce some waves like sounds. So instead of that, we can replace the Li-Fi technology. And coming to that, we can also integrate both the Li-Fi sonar in a hybrid model, as well as we can switch to sonar when we need, and also we can switch to Li-Fi technology when we need. So this is the proposed methodology recently we have done. Next. So, as per the research findings, we have done a high data transmission and cost effective solution because we are using LED, improved reliability, and data is accurately transferring from transmitter to receiver, and a lower power consumption, secure communication, and there is uh, minimal interference and eco-friendly because it's a light, there is no harm like sonar we use before. So coming to the conclusion, I would like to conclude with this project like that Wi-Fi technology and that improves our communication systems. Present we are using submarines. There is a different type of acoustic uh, acoustic communication and laser, Wi-Fi and microwave technologies, and we can make some more improvement by this systems. And the future scope is that we can integrate AI as well and smart sensors to improve the communication between them. Thank you. So I would like to receive more.
Yeah, no, no. Uh, First, I would like to know what is your work.
Sir, actually, we built a small prototype recently.
Okay.
So the data and audio we have transmitted from one side to another side. So it actually we done recently.
So, any photos or anything?
I have uploaded in the class. As
Okay. What is the distance you checked this communication?
So
Prototype
below 1 meter switch.
below 1 meter.
Yeah.
So, whether it is a short.
Actually, if we use laser, it will be increased at some distance, like more than 10 meters, like that.
Okay. And what is the necessity to make a hybrid model of all the sonar, the LI, and this?
So actually, the water consists of there will be some clear water in some spaces, and there will be muddy water some spaces. So we don't know what the situation like. So you can actually switch while required. Like sonar, it affects it transmits the echoes from into the water. So actually, in that cases, muddy water, a sonar will be helpful. Coming to the clear water and somewhat plain water, we can use Li-Fi technology. Light will be emitted and also laser we can use.
What is the advantage?
Advantages is that we can use Li-Fi is a better one compared to sonar, and also sonar is one of the uh, like drawback for the whales and some other aquatic system which affects the partial stress to them, and also there will be some distractions while receiving the signal from transmitter.
Okay, thank you.
Thank you.
Thank you so much for presenting. May we now have the authors of the paper ID 198.
Thank you so much for the presentation, guys. How are you planning to overcome the line of sight challenges in between
Actually,
between the transmitter and receiver? And what do you think about the attenuation? Like, be it fresh water or be it muddy water, the attenuation will happen. So, how would you make sure that the data reaches through right?
actually coming to the line of sight, Wi-Fi will be a uh, distraction for the line of sight. In that place, sonar will be used. As we recently said that the, we can overcome the situation by implementing the hybrid model.
But don't you think shifting will make sure that data packets get lost? Because when you are shifting in the hybrid mode, the data packets usually tend to get lost. So, how would you overcome that challenge?
Of course, there will be a loss of some data packets while transmitting and receiving side. So actually, we look forward for this.
All right, all the best.
Thank you.
Thank you so much. May we now have the authors of the paper ID 198.
improve the communication between them. Thank you. So I would like to receive the form. First, I would like to know what is your work? Sir, actually, we build a small prototype SUV. Okay. The data and audio we have transmitted from
Good afternoon. My name is Anupama James. I come from Chinmay Vishwavidyapit, and we have Dr. Felix and Philip. He's as an associate professor with the Jain University. So here we have our paper titled Intelligent Arctic Zooplankton Counting and Classification System. We are comparing a few of this AI-based classification systems. That is, we have done a comparative analysis. So introduction. So plankton. Plankton are mostly tiny organisms that drift through the ocean, carried and dispersed by the tides and currents. It's very, very tiny organisms. Few of them are microscopic, and there are trillions of them in the ocean. So the zooplankton serves as a fundamental component of marine ecosystems, acting as a primary food source for numerous organisms. We have many zooplankton sampling techniques which is traditionally in use. It's from research vessels or ships we can put this net and or the satellite data actually it's not possible because zooplankton cannot be observed from a satellite. So we have traditional methods. So what you can see here, from the ship or a boat, you can put the net, this zooplankton net, and you can collect the sample. And this sample should be analyzed in the microscope. And from this microscope, you can identify the species. This is what the traditional method we used to do. But now it is changing to the machine learning based system where you can put this machine learning, we can put the samples under this machine learning classification system where the machines will classify which species it is. So these are the examples where the people have developed many Arctic zooplankton monitoring systems with the AI. It's mostly from the other nations it coming. The US based Zeus glider is there. Zoo glider is actually an ROV. Attached in front of this ROV, there is a device. That device will capture the image of the zooplankton and it will analyze and give you the classified species. Then we have the image. These are the other video plankton recorder, ZooScan. ZooScan is from Germany. It's actually where this is like a photostat machine where you put the sample underneath and you can take the images of this particular species. It's microscopic organisms. You can take the images. So this is a comparative study what we have done. There are a lot of AI-based zooplankton monitoring systems. A zoo glider, that's platform, it's AUV, and the imaging technology what they are employed, like optical and acoustic sensors used. Then AI integration, what kind of AI integration has done there, and what are the advantages. So you can see deep learning, morphological analysis, and AI assisted classification, and CNN-based classification. These are the technologies they're using in the latest AI-based zooplankton systems. Next slide. So the back problem statement. Okay. So this is our problem statement. Conventional zooplankton identification and methods are labor intensive and lack of real-time processing. So need for an AI-powered automated classification system that provides high accuracy and real-time species recognition. This could be low cost. This is what. And why we are into this? Because actually we are part of the India's Arctic Expedition Program, and as part of that, we will go to the Arctic region and we stay in the India's Arctic research station called Himadri. So we have to stay there for a couple of weeks, and we will be sampling the data. We'll be collecting the samples from the Nialsund, that is the Arctic research base. So we'll be taking the data or collecting the actual data from the Norwegian Arctic research base. So here, So this was a team we selected and we went to September 2024 intake. And we stayed for 1 month and we collected the real data with our device. So could you please change that? So this is a device we have developed for that particular data, particular data collection and analysis of the sample. So where we can see we have also deployed, this time we have applied the traditional method where we deployed the net and we could collect the sample and the collected zooplankton sample we poured in that container and in front of that we have arranged some LED array for lighting and a 4K video camera we placed in front and with that we took the images and we have processed with a Beagle Eye AI module. So with the Beagle Eye AI module, we have just processed the data for classifying the images. So this is a battery management backup also we have. So this is a proposal methodology where we will get the annotated images for the training and annotation, training and testing. Then we use the CNN blocks. But for this size is very small and microscopic. So what we have done is like we use the FM network multi-scale thing to just enhance the quality of this, and then we predict it, and we classify the particular zooplankton species. This is how we do the explain. At the right side, you can see the device we have developed for the particular study. So there's two chambers are there. In one chamber, we pour the Arctic zooplankton sample that we collected from the Arctic region. Then the second chamber, you can see the camera and the apical bone setup, and attached to that there is a monitor where you can where you can check the real time monitoring of this species and identification. So this object detection, this next slide. So next. So this is a system overview that already I have explained. Normal image and we take the microscopic image. This is a live organism. So we take the normal image as well as the microscopic image because it's few are the microscopic. So at a time we are processing both. So if it is a microscopic image, we directly for the classification, that's possible. But it's a normal image, we do the object detection module as well as the object density estimator. Then we go for the, then we compare it and give you the species. So this is next slide, please. Next one. Next. So these are the research finding. So we achieved an 86% of the classification accuracy and we are done implemented with the YOLO as well. So we compared with the YOLO V5 version which we had done previously. So it is showing a comparatively significant of this significant higher accuracy in this method. So this precision and recall is also came out well and real-time zooplankton identification was possible and then this enables a continuous ecological assessment as well as minimize the human intervention. That's a plus point. These are the species we have identified from the last visit. So these are the name and species and of the zooplankton in the Arctic region. It's very important because it is the first chain of the food web. Okay, so this is a result. And can you go back to the first slide? First. Second. Okay. So here you can see the zooplankton is in the right side picture. You can see in the above surface you can see the polar bears, seals, and all the organisms. Out there is a phytoplankton. Phytoplankton is the first food web thing. That is the due to the sunlight, the phytoplankton is like a most kind of an organism, a small plants kind of thing. So zooplankton will eat this phytoplankton. Then fish will eat this phytoplankton, zooplankton. Like that it goes. So about that. Okay. So this is our study. This was for the last year Arctic expedition. And this year what we are planning is we are developing an ROB. And in this ROB we need to attach a low cost image based system that could achieve good result for this zooplankton identification as well as the abundance because it's very very important for our ecosystem and the climate change. Okay, that's all. Thank you. AI module, we have just processed the data for classifying the images. So this is a battery management backup also we have. So this is a proposed methodology where we will get the annotated images for the training and annotation, training and testing. Then we use the CNN blocks. But for this is a this
On the comparative study, you said something 86% and 79%.
no, that YOLO and our CNN based.
Okay.
So this is actually the existing systems where AI integration is happening for this supplanted monitoring device. So in other like US, Germany, and all other countries, they developed some systems with AI integration for the supply. In India, right now, what we are doing is like our scientists are going to the going in the board. They're deploying the supplanted net. They're collecting the sample. So with that sample, they come with they put the formalin. They bring it to India. They put it under the microscope and they identify the organism. That is how they do analysis of this. So
Oh my, first means that 86% and 79%. Either with the same data you are comparing or
YOLO is so this object detection. This next slide. So next. So this is system overview that already I have explained. Normal image and we take the microscopic image. This is a live organism. So we take the
So
normal
much for
image.
presenting. Class, we will invite the authors of the paper ID 290 to present their book.
Processing both. So if it is a microscopic image, we directly for the classification, that's possible. But it's a normal image, we do the object detection module as well as the object density estimator. Then we go for the, then we compare it and give you the species. So this is next slide, please. Next one.
My name is Amit Pawar. I'm from IIT Madras. My topic name is AI and Power BI approach at data analytics and ocean forecasting using Mood Boy. Next slide, please. So let's get some overview regarding NIOT and my department. So NIOT is providing good oceanic research, oceanic findings and advanced ocean science. And in NIOT, one of the department is ocean observation system, which gathers various types of data called meteorological, climatological, and environmental for various research purposes. So the image shown is the actual Omniboy, which is from the NIOT, which is recording the meteorological data. Next slide, please. So regarding the problem statement, reliable predictions from meteorological data are also crucial for early warning systems. But traditional methods do failures due to sensor failures, missing values, and anomalies. So we are using advanced data analytics tools and advanced machine learning methods for providing the good predictions so that we can use it for various early warning applications. So our objective is regarding the data analysis by using advanced tools. Also, we are using advanced machine learning methods and deep learning models for the proper predictions. The actual image is showing is our Indian coastal region where our various Indian buoys are located, where you can see various types of buoys. So for our this paper, we are analyzing AD07 name buoy. So next slide, please. So regarding the literature survey, we have followed three research papers. First research paper follows various machine learning models for wave elevation based on the air gap responses. The second research paper follows a wave analogy like a pitch hue response machine learning models. And the third research paper used the meteorological data for various machine learning models for getting the predictions. Regarding the methodology, first we are collecting data from the buoy, then we are doing data processing, then we are analyzing the data in the Power BI, then we are using feature engineering, predictions like model predictions from LSTM, then we are comparing various models with the LSTM for getting the good idea. We are getting the accuracy scores. After getting the accuracy score, we are refining it whether they are good or not. And after the last stages, we are forecasting the output. Next slide, please. So you can play the video. So you can see the advanced data analytics tool called Power BI. It is the one of the most advanced tool for data analytics, where you can see we can analyze various yearly data where 2022, 2023 quarterly analysis we can do. You can see at the image we can analyze quarter two data. We can analyze monthly data, yearly data, quarterly data, as well as daily data as well with use of this software. The main advantage is once we created the dashboard, we don't have to analyze every day. We can import the file from the section where we can importing various types of file, Excel sheet, comma separated value, etc. Where we can also integrate with the SQL server. So after integrating with the SQL server, we have to just import the file so that it can analyze the future data. So it will we will analyze within the few minutes. So this is regarding SQL. Next slide, please. So this is the prediction that we are following. We are following LSTM model. Why it is good? It provides well with the noisy data, scalable to large data sets, long-term dependency. So image shown is the blue graph, which is actual historical data, and orange graph is the prediction data, where the red dot values are the weekly average values and the green dot values are the weekly predicted values. The down graph is for data validation. For data validation, we have divided the data into 95% and 5%, where we are comparing that 5% data with the actual data, where we are getting percentage error of 0.44, 0.11, 1.5% only. Next slide, please. So after pressure, we are again analyzing two more parameters called pressure and wind speed. So same methodology that we follow for this as well. So we can go for the next slide for the actual results. So the result section, you can see for pressure and temperature, we are getting good results. But for wind speed, we are getting drastic changes like percentage error is about 280%, 114%. So wind speed is getting error because there are a lot of sensor anomalies and sensor failures in that. And we are working on that wind speed analogies. So regarding the final accuracy scores, it's pressure, temperature, and wind speed. We are getting 1% error, and we also compared with the other algorithms called ARIMA, SARIMA, XGBoost, and LSTM for pressure and temperature. But for both pressure and temperature, LSTM provides a good results, which are 1.62% and 1.32%. Next, final conclusion. Regarding the conclusion, we are seeing the pressure and temperature are providing good results, but for wind speed, we are again analyzing it, and we are going to analyze meteorological parameters for various purposes. For future research directions, we are again analyzing relative humidity and ocean currents for further research, and again we can explore more models like GRU, gated recurrent unit, and CNN LSTMs for further performance. So future applications are we can use it for early climate analysis, search and rescue operations, marine and offshore safety, and navigation and logistic operations. Next slide is the references that I have used for my paper, and thank you for patiently listening. I am happy to answer all the questions.
Good afternoon. Thank you so much for the presentation. Could you please throw a little bit more light on the type of advanced machine learning and deep learning models that you use?
Yeah. So advanced machine learning methods like we have analyzed compared four models. Basic models are ARIMA, SARIMA, XGBoost, and the advanced machine learning we are going in the deep learning model where we are using RNN and LSTM, where it is used for large scale data sets, where it is a little expensive, but we need more accuracy for early warning systems. So that's why we have used the advanced machine learning. So we have integrated LSTM plus XGBoost. So two combinations of algorithms. That's why.
Also, how easy it is to integrate any additional parameters to Power BI as compared to other visualization tools?
It's very easy. So if you go to Power BI slide, huh. So there are a lot of options. You can see get data insert. In that insert column, we just have to add column, or in that get data column, we can integrate with the various files. We have to import file via SQL queries as well, and we can import manually by Excel sheets as well. So it is very easy to import new data sets. Yes, thank you.
Thank you so much for presenting. Now, all the presented paper will be reviewed and evaluated by the session chairs. Result will be announced within 5 minutes based on the assessment of the innovation, relevance, and the clarity of the presentation. Now, on behalf of SRM Institute of Science and Technology, we would like to express our heartfelt gratitude to our respected session chairs, participating authors, and the audience member for gracing the session with your valuable presence. We deeply appreciate your time, efforts, and scholarly contribution towards this meaningful dialogue on the technological advancement in ocean sciences. We look forward to continue collaborating and impactful research in this vital domain. At this moment, we would like to invite our esteemed session chairs onto the stage to express our gratitude and appreciation. We request Dr. Preeta Roslin Ma'am to kindly present the mementos as a token of respect and sincere thanks to their valuable presence and guidance throughout the.
We can importing various types of file, Excel sheet, comma separated value, etc. Where we can also integrate with the SQL server. So after integrating with the SQL server, we have to just
Dr.
ensure a value
Sahasraj
so that
sir,
it can analyze the future data.
let's
So
take
we
the
will
session
we
checks.
will analyze within the few minutes. So this is regarding SQL. Next slide, please. So this is the predictions that we are following. We are following LSTM model. Why it is good? It provides well with the noisy data, scalable large data sets, long-term dependency. So image shown is the blue graph, which is actual historical data, and orange graph is the prediction data, where the red dot values are the weekly average values, and the green dot values are the weekly predicted values. The down graph is for data validation. For data validation, we have divided the data into 95% and 5%, where we are comparing that 5% data with the actual data, where we are getting percentage error of 0.44, 0.11, 1.5% only. Next slide, please. So after pressure, we are again analyzing two more parameters called pressure and wind speed. So same methodology that we follow for this as well. So we can go for the next slide for the actual results. So the results section, you can see for pressure and temperature, we are getting good results. But for wind speed, we are getting drastic changes like percentage errors about 280%, 114%. So what is wind speed is getting error because there are a lot of sensor anomalies and sensor failures in that. And we are working on that wind speed analogies. So regarding the final accuracy scores, it's pressure, temperature, and wind speed. We are getting 1% error. And we also compared with the other algorithms called ARIMA, SARIMA,
For our
XGBoost,
next
and
session,
LSTM for
we
pressure and temperature.
request Ms. Priya to introduce Dr.
So for
Sanasi
pressure and
Raj.
temperature, LSTM provides a good results, which are 1.62% and 1.32%. Next
Good
final slide,
afternoon,
please.
everyone.
Regarding
It
the
is my
pressure,
great pleasure to introduce our distinguished
so for
speaker
pressure,
for
we are
today's
getting
session,
good results.
Dr.
For
Sanasi
wind
Raj.
speed, we are
He
again
holds
getting
a
good
BE in Civil
results.
Engineering
And
and Master in
we
Civil
also
Structures
provided
and a
some
PhD in
specific
Ocean Engineering. He is currently serving as a professor and head of the Department of Ocean Engineering at the Indian Institute of Technology, Madras.
providing a relative
His
value
area of
prediction for the temperature
specialization are vast
and
and impactful,
expectation
including
for the
wave
current
hydrodynamics,
unit. And
wind
also
wave
we
modeling, numerical simulation of nonlinear wave structure interactions, and coastal erosion and protection. Since 2003, Dr. Sanasi Raj has completed 14 research projects and has led over 200 industrial projects ranging from port and harbor design to intake and outfall systems, coastal protection structures, and wind wave prediction models. His expertise continues to play a vital role in bridging gap between academic research and real-world coastal and marine engineering applications. We are truly delighted to have him with us today. Please join me in extending a very warm welcome to Dr. Sanasirat sir.
could you please throw a little bit more light on the type of advanced machine learning and deep learning models we use? Yeah. So advanced machine learning methods like we have analyzed compared four models. Basic models are ARIMA, SARIMA, XGBoost, and the advanced machine learning we are going in the deep learning model where we are using RN and LSTM, where it is used for large scale data large scale data sets, where it is a little expensive, but we need more accuracy for early warning systems.
Thanks for
So
the introduction. And
that's why we have used the advanced machine learning. So we have integrated
so
LSTM
I'll
plus
be talking
SRM
about uh,
plus XGBoost. So
something
together we are
relevant
using
to the main
that's why.
theme of the conference in the sense that if we talk about AI in our machine learning,
How easy
main
is it
important
to
part is data.
integrate programming
How
languages
well
like
we interpret
C
data,
compared to other
how much we can explore the
it's very easy.
physics,
So if you go to
all are
Power
very
BI,
important. So
Power BI
by
tool,
default, all of us are
simply using Google Maps. If I'm coming from IIT Madras to SRM, if I put the map, it shows today 1 hour 8 minutes. So nearly 1 hour 10 minutes I reach here. And that's the beauty of the data collection done by the system and how it interprets. So obviously we are putting a bigger umbrella. Over the decades, this data analysis has evolved and named in different sense. And obviously we are using the state of the art artificial intelligence and the machine learning. And by default, the underlying principle is the statistical. And starting from average, RMS, skewness, kurtosis, then creating a large database of TensorFlow. All these things matters a lot. And how we explore more than a statistical sense. Say neural network was very popular in 90s and 2000 plus, where we try to adopt something more than a simple statistical techniques. Now artificial intelligence has come one step above that. So neural network, even though all the tools that we are using, say fast forward or backward, etc., neural network, all are subcomponents of the artificial intelligence. So all the modules that has been developed over the decades are part of the artificial intelligence over that we are building up all our systems. Now I'm going to talk about ocean waves particularly. One important thing is not that I'm going to make some method where I'm going to claim that what we are doing is better, but I want to emphasize, particularly for the students, while you are using AI, if you utilize it blindly, ultimately there is no point in doing in a better manner. Say Google Map is doing very good work. It's not that just interpreting the data. It does logical sense. And if I start from one point, Chennai to Trichy, and by the time entering the Trichy, it analyzes the past few days data, what would be the traffic at that time. It won't analyze the present date. So all those things has to be done intelligently. That's what the artificial intelligence. So that algorithm you have to choose according to the requirement. I cannot use the same algorithm that a Google Map is doing the route map from one location to another location for my ocean wave prediction. I have to use a different algorithm. So even though AI is a bigger umbrella, we have to use a proper algorithm we have to choose. That's a very, very important based on the data set. Now coming to the ocean waves, all of you have come across the ocean waves because which whatever you are seeing, that's what the waves I am going to talk. And one important aspect in the ocean environment prediction of the waves itself, waves has a short memory. But same thing, if you take about tide, even without using artificial intelligence or without using any model, even after 100 years, with simple equations, because tidal coefficients are known at any locations, we can predict after 100 years, say for example, 2100, say April 17, at 3 p.m. What is the tide? I can say, I can tell now with 100% confidence. Because that's a full cyclic between attraction between the celestial bodies to the earth. Next, coming to the current. Current also phenomenon in which, and with more or less with 90% confidence, we can easily predict what could be the current during the, say, August from today. But ocean waves, it's highly dynamic. The memory is short. Memory is 2 to 5 days maximum. So if you use the past data, how you effectively utilize the algorithm? I put that algorithm under the AI. How effectively we are going to use? That's a very, very important one. Now, having just brief background, and I just differentiate the data-based and data-driven model. The main difference is most of the tools that we are using day-to-day life is a data-driven modeling where they don't depend on any other systematic modeling or physics-based models, where only data are being used to interpret and give the output. But here, what we adopt is a data-based modeling because of the very short memory of the ocean wave prediction. Building a physics-based model at background and improve that model prediction with the data. That's the approach has been taken. Because predicting the ocean waves of very, very great importance. starting from ship navigations to the even to the tourism purposes, where many of you would have seen at many salient beaches, many places they put the red flags, where you should not venture into the sea because it will pull you into the sea. That can be easily predicted if we can easily predict the wave direction. And we have there's a convergence zone where ocean current will pull us into the sea without even whatever the great submarine got. So that's what the wave prediction is very much important. So database model. So we have a physics-based model as background. So the final error band has been adjusted using the measured data. So measured data is obviously here now it's a wave height, wave frequency, and wave direction. And of course, given a more data and more precise output we can get. And however, only the problem is that it is computationally expensive. Time we are not going to reduce, which most of us wants the output immediately. That's the only drawback. But most of the assumptions made in the physics-based model can be overcome by the data. But data-driven model, we are not depending on that any of the physics-based model. So we can get a very good output, which is possible when the memory of a particular data set is been inbuilt. So on both aspects, AM or neural network, machine learning, all these algorithms under this one are common for both. How effectively we are going to replace the important thing. Now coming to the very specific thing, what we have done it, and we integrate database models with the numeric modeling systems with assimilation. The word I'm trying to keep the assimilation because even though we are going one step forward than the assimilation term they utilized in 90s. Because now we are also trying to use the latest prediction tools to integrate with the earlier ensemble based average. And finally, ultimately, the output will be very important for to take many of the management decisions. Now, coming to the data assimilation, if I'm keeping the word in the data itself, 100% we can give the confidence, assuming that we are measuring a very good data sets. But the problem is that data is only discrete. Even if I'm opening my Google Map, if I'm traveling from SRM to say Sengalpattu, and every minute my spatial data is going to change it, and the information given to the Google Map is different. Spatial as well as also time is very sparse, and but it's more precise. But if I have a physical model background, I have a very high resolution in space and time because I can produce that output anytime, and it is quite cheap. Today's computational power makes any computational modeling system to solve it very quickly. If effectively place, say for example, even graphics card, if you effectively program it, you can do it faster. But there are many model uncertainties. Combining these two make a assimilation to a module that combines these two gives a better thing. And if I take up this physics-based model, so more complex energy transport equation that we solve to predict the F is the spectrum wave, that's nothing but the wave energy. If I predict, I have to solve many of the physics-based system. How much energy is or momentum is transferred from wind to the ocean so that waves can be generated. But waves also break, that means energy is dissipated. And during the propagation, two frequency components merge and it will form a long waves. All those things are very complex and particularly the nonlinear energy transfer term is more computationally expensive. If I remove this term, it will run like much faster than a data-driven model. But without that, the waves will not grow. So that's what definitely I will be needing that. So I'm not going to much details about it. So if I want to solve this one, it has a lot of uncertainties. We have each and every term here. How much wind is transferring momentum? I have the uncertainty. How much waves are going to break? This has uncertainty. We are going to express only in terms of probability sets. With the nonlinear energy transfer, even though mathematically we can solve it 100% perfect accurate solution, but because of the computational expensive, we make an approximation. Now, so we set up the model over the entire Indian Ocean, which encompasses both Bay of Bengal and Arabian Sea. And if we do the prediction, and this will be the typical snapshot of wave height distribution in, I think, in July during the our Indian Ocean, Bay of Bengal, Arabian Sea. Just a snapshot so that what we try to improve. Now, this wave height distribution, there are many inaccuracies. We try to improve it. Now, what we have taken, our model is a deterministic model. It has a four major components. Because you have to identify which component you want to improve, which is very important. One is input, which is the wind here. There are many state variables which are kind of what we call the spectrum. So energy content at each frequency band, yes, spectrum has a, so nearly if I take 12 wave directions with the 25 frequency component, I will be having about 300 variables in a particular spectrum. Then parameters. The friction coefficient is one parameter, both surface friction, water friction. So many parameters are in the model, which is common because that's what I put. Not wind wave model, it's a general any deterministic model. Then output is our wave height, wave direction, wave frequency, and this is a typical system. Now, if I want to input a wave height measured from satellite or the some physical measurement using buoy, then I have to add an updating procedure which can update either the wind that is possible and what is the algorithm chosen at each stage will be different, or we can input energy itself or parameters or the output itself without going into the any of physics maths model. By doing the output, we have the advantage of the keeping the model run same so that we can also save a lot of time. So that means updating the output is similar to a data driven models integrated with the background information. So each one has its own pros and cons. But if I only update the output, that means the energy balance in a particular system is not met. Anyway, if you are very keen on the energy balance, then we should not update the output. But here we are sacrificing the energy balance on computational expensiveness. So we took it forward. So a typical model is wind driving the model and the output is the wave height. And now adding an algorithm, that algorithm I will explain in the couple of coming slides. Either with the satellite wave measurement, satellite we have abundant data. Whatever the data, particularly the ocean or the land side, we have abundant data, which is not even when the 0.001% of the data that has been collected, we are not utilizing it. That means we have a lot of opportunity in the AI to bring out the actual physics behind the data sets. So satellite wave measurement or even the physical wave measurement, then we can improve this model. Now, what we are trying to do is we chosen this is the output and we took from numerical model output and satellite. Particularly satellite has a two type of measurement. One is altimeter, will give the integrated energy. The second one is a SAR data, where spectrum itself we can get it. Both things we try to do it. So by doing so, our wave prediction will be much better. I will come back to these details around. Yeah. So assimilation or the data driven model or database model in this particular case, if I take the altimeter reading, I get a single number which is nothing but the summation of the spectrum. Where for spectral data, each and every frequency band I can improve. So each has some pros and cons. There are different tools. All these tools are also part of the so-called machine learning at present context. And most of the algorithms, they use simple interpolation methods. Whether you know or not, by default it chooses a simple interpolation. Unless if we choose a higher algorithm, we cannot utilize it but much better of it. So variation methods, sequential methods, and many methods are there where we try to take the sequential method. We are, even though it's a short-term memory, and every time step update is very important. Now, what we try to see is that instead of waypoint itself, we try to improve only the errors. That's a one way where already I have 80% better estimate. Why I have to disturb this 80% information also? Keep the 80% information, say, or only update the 20% error induced part alone, why not be updated? So that 80% already I have a confidence. So that's the thing that we adopted is we are slightly changing the concept before adding to a database modeling. And this is a simple sequence of the equations, three. And everywhere, if we see, there will be a one distribution or error distribution or information distribution matrix. How best we get this information distribution matrix? Gain. Here it's called the gain. If I use the common filter, it's called the common gain. Whatever the different algorithm we use, it is called the gain of different name. Now, if you adopt a different K, say neural network also I can get it. Different algorithm we can get it. And but this equation is simple. So this is a model predicted one, and this gain taken the values of the measurements, that is the data. Z is the data that already we have abundant data, and data minus what's the best available in the particular data. That means this is the error. Data minus the model prediction gives you the error in the model prediction, and I only distribute the error to all the locations. Data is at only one point. I can distribute that information using this gain matrix to the entire domain. That's what how good we are getting this gain. This is only a trick gain most of the systems, which includes our root prediction. And what we try to do that is we try to make a large ensemble, and the concept is very simple. Yeah, it's called a perturbation. When we perturb a particular system, it perturbs it from its actual state and come back to its natural state. And every second or every microsecond, if I monitor the perturbation system, then we can find out how the information is going from one point to another point, which is nothing but we take the natural frequency of a particular system. But here we don't talk all about the natural frequency because domain is very big and the variables are much larger. So this K is being done using the simple ensemble covariance. This while making ensemble covariance, it is both time and spatial varying. And if you make a both time varying spatial varying, it is called the common filter. Without the time, even the common filter is a very old algorithm or which was established much earlier. Even artificial intelligence, they don't utilize the full common filter way. Yes, even now we are making it very much simplified. So common filter is been very powerful. Now I go back and just highlight and what is being measured. Yeah. So at every time step, and the x-axis if we say, assuming the time step 1, 2, 3, 4, etc. Every time step, and if I have the measurement, say for example, this dotted line measurement, the bar here gives given measurement, we can also give the uncertainty. So any data also can have uncertainty, that also we can consider that. So continuous line is the model prediction with the dotted line is the model uncertainty. Then before going to that part, this measurement coming to the picture, measurement is lower than the model. So I drive the model down. Then going to the next step, similar one. Next step I have again model is less. Then I drive it. Then I push the model down. Next. If similarly I go at every time step. Now here model uncertainty is more. the bar of the model result is more, because then I will not give any importance for the model now. So, sorry, observation, because it is the measurement data. My data has a lot of uncertainty. So, data will not be given any uncertainty. So, same logic is being applied in any algorithm, which includes the so-called the machine learning at present. So, using the same way, every step is being done, and this G. So, the gain or K or G, K and G are both are one and the same, and simple expressions are made either in terms of the covariance, or this can be easily replaced with neural network or any system with same variables under the names, and we can cast the K and G. Now I come back to the initial slides where the what this wind input and waves are predicted, and if I extract the information at one point, assuming that couple of points we choose within the data, couple of points, particularly we are choosing the Bay of Bengal at two locations, and where I have the data in hand, GUI data, that's a physically measured data. So if I take it, predicted is a continuous line at the bottom, black line, observation is a red line, and the simple, the so-called, here we averaged out over the time. The next few slides I put time also a variable for us. So the blue line is a updated one. So model is getting updated. So this is the data driven or database modeling system. Similarly, that is for the next one. So the previous two graphs are given in the scatter diagram. So while the scatter at the shallow water wave buoy at 3 is very much scattered, and database modeling drives towards the much better fit. Correlation, good correlation will get. Now, that is possible when the GUI data is there, where GUI data is at single point, but time series. But estimated data, many of you know that satellite is going with the at tracks. So, same track, it will come back only after 2 weeks. But if I have one data at one location, same location, I'll get the another data after 2 weeks. So, this information also, we can effectively utilize it spatially discrete, time also discrete. Both spatial and time discrete information, if we capture it using the same logic, we can improve the entire domain. Because any data, I'll show you in the next one. So, any information at one point will be transferring the information to the downstream. If the wind is from left to right, say here, if I'm point of reference, if I'm making a measurement, this measurement will helpful for the downwind, not in the upwind. Yes, this carries the information of this wind, and this will telecast to the any other point on the downwind. This is the wind, it's coming. Be careful. So same logic, we try to take these red points are so-called the observation station, and how this information is spread. So if my observation station is here, and this is a wider domain where information is passed from this red point to all the domain. Same thing, if I choose a red point on another location, this information is chosen on the very small location because it's a northeast monsoon. This is southwest monsoon type. So very less transfer. Same thing, red point is here, red point is here, very close to the coast. It is not transferring. But now there is a gap and data transfer is here. This may not be meaningful. We have to do the unwanted data updates. So all this one also important because we have a discrete data, ultimate data at different point and different time and different spatial locations, and every time our K or G, the gain has to be adjusted. They're using this so-called this is the K. Actually, this is a plot of the K or G gain matrix. Each one is a gain matrix. Every point we should simulate a K or G. If you already have a prediction measured already, and update will be a quite straightforward. We use only data to just update the model similar to any other AI tool. So this is for different stations, how we are doing it. Say observation is the black dotted, updated is the red, blue is the blue dotted is the model. So model to updated observation is used to update it. Now this is again the scatter diagram of the same. How we steer the observation is steering or the data is steering the model prediction to a better prediction, and this is kind of a RMS error or mean uh, absolute mean average or the root mean square error. How much it's a better predicting at each location. The wave gate. Here I have taken only the wave gate. It also same to a wave frequency and wave direction. So in a nutshell, same method, I cannot use it for the tide because I don't need here so much cumbersome for a tidal data where the predictability is much better. Same thing current over the every month average current is very much predicted. So different data sets, what is the variable? Say traffic data if you say is highly variable. And say but Sunday traffic I can map it to the Sunday of any Sundays of the particular year. But vacation time it will vary. So that intelligent data set can mathematically be created. That's what we are effectively utilizing the machine learning, and how you are storing the data to the system. That's also another task. How you are storing or where you are storing. So this is what just in a nutshell I am trying to give it. And probably if you are interested, I can share few of our publications. You are welcome to interact with us. Thank you.
Thank you, sir. We do request Dr. Sridhar, HOD of EEE Department, to solicit.
I have a question. When you're doing the prediction for ocean wave height, in what way the machine learning models are overwhelming response, producing overwhelming response that the conventional approaches?
First of all, our basic logic, machine learning or artificial intelligence is a bigger umbrella. It encompasses all the areas of it. So machine learning model, it is learning from previous experience more than the just statistical sets. That is the information like a neural network. Neural network also doing one step forward, that is statistical thing. Machine learning, we are doing one step further, getting the information, say, for example, what we do here, machine learning technique is seasonal average. We give it an external input. So if it is running for July, same gain matrix, it will operate in a different sense. Because of the sponsor. But in November, same gain matrix, we will update with a different factor because we learn November our my wave climate in Bay of Bengal is different way. So we adjust the gain depending on the seasons. That is for the waves. And for different things we can make it. So how it's different is how logically we can make it. And I add three algorithms to go together. What are those three algorithms are very important for wind wave modeling, whatever I adapted. We cannot use it for the different data sets. That's what I said. Even for within the ocean itself, every variable is a different, unique. So we have to understand and use the algorithm. There are hundreds of algorithms out there.
That is how the validated with the observed data.
Now, of course, observation is there. Always we take 20% of observation as a spare without we don't use it for update. And that 20% data is used for our validation. Whatever the prediction is being compared where without those data we don't use it for only we use it for comparison.
Cases, suppose we are doing future predictions, where at that present we don't have the observed data, but naturally it is going to happen in some days. That time, whether the data is collected and then it is checked with the model, in that case also it is validated.
Yeah, that's also we do it normally. That is only for academic purpose. But in actual practice, if I do the forecast data, how better I do, then only I will be approached the next time. For example. So academically we do it, but actually even we are also doing it. Inca is also we are working. We transfer this assimilation model to them. They are also testing it before giving the information to say fisherman and others.
Microphone.
Good afternoon, sir. I have a question.
Yeah.
I'm here, sir. I'm from Incois.
Yes.
Sir, I'm into hydrodynamic modeling using my 3 software. So I would like to know, as far as the hydrodynamic modeling is concerned, whether we need to include the wave radiation stress into the computation. So how these waves can contribute to the wave current interactions.
Mm, current in the open ocean, current is very less. Okay. And normally, only very near the coast where sediment transport or the oil spill is happening or some mixing is happening, where we have to add the wave induced stress, that's called the radiation stress, into the current. Otherwise, it's not required. In the open ocean, say mid of the Bay of Bengal, wave current interaction will not play any role. Even though there will be there, it has a insignificant affecting each other. But very near to the shore, we take the radiation stress from waves, we calculate, and explicitly it's added to the hydrodynamic,
Yes, sir.
not on the other side.
For that, we need to compute the wave radiation stress from other model like spectral wave module.
Yes, correct.
So if I don't have that module, then from any other source can I improve the wave radiation stress?
But if you already have that spectrum in hand, without model, assuming that every time step, every spatial information, if you have a spectrum in hand, then you can easily calculate the radiation stress. You need the output from somewhere.
Yes, sir. Yes.
Even if you are not simulating, you should need your output.
But we don't have the updated license of that spectral wave module. Only we have the updated HB module. So can we take from the previous version from where we can generate the wave radiation stress?
Very much, very much. Because the update they do, Mike 3, they do only, most of the updates are only in the post pre-processing.
Yes.
And the basic physics, they don't fetch. Even basic physics in Mike 3, they are not updating like Wavex 3. Very old update. Still they are giving. Still older version you could use.
Right, sir. Then, as far as this SAR spectral you are getting from the Sentinel datasets, how you are expecting the spectrum using the Sentinel datasets?
And we work with the SAC. So they extract the spectrum and give it to us. We don't work because that algorithm they give because that is actually delivered to them. SAC. Last year we completed work. They give the SAR spectral data in a particular domain.
Fine, sir. Thank you.
Sir, we request Dr. J. Preetha Roslin to felicitate the memento to Dr. Sanna Siraj. We're taking a tea break, 5 minutes. Please return within 5 minutes. It's in the back.
Yeah. Yeah. Okay.
For our next session, we request Ms. S. Sujata to introduce Dr. Pooja Mahapatra.
Behalf of Department of Electrical and Electronics Engineering, SRM Institute of Science and Technology, it is my great pleasure to introduce our distinguished speaker for today's session. In a room full of bright minds and kind hearts, it is truly a privilege to welcome someone who exemplifies both brilliance and compassion, Dr. Pooja Mahapatra. Dr. Mahapatra currently leads geospatial and remote sensing solutions at FIGRO, where she has been instrumental since 2019 in commercializing a variety of cutting edge innovations. Her work spans impactful applications from coastal resilience to railway track maintenance, directly contributing to critical infrastructure and environmental sustainability. She is also an active member of the Disaster Resilience Working Group of the World Geospatial Industry Council, where she channels her expertise into global disasters and response initiatives. Prior to her time at FIGRO, Dr. Mahapatra served at Shell 2016 to 2019, where she led global efforts in deploying and replicating advanced technologies in the geospatial domain, while also offering internal consultancy in remote sensing, geospatial analytics, and geodesy. She earned her PhD from Deaf University of Technology, where her research focused on satellite remote sensing for ground deformation monitoring. Her dedication to applying geospatial solutions to real world challenges earned her place on Geospatial's world list of 50 rising stars in 2022.
a recognition that speaks volumes about her impact and promise. It is an absolute honor to have her with us today. Please join me in warmly welcome Dr. Pooja Mahabhadra. Thank you.
Sometimes just leaving and joining helps. Okay. Good afternoon, everyone. It's been a long day for you, so I hope that you will still have the patience to listen to my pitch here today. Let me share my screen. Are you able to see my screen? Are you able to see my screen? Hello, do you hear me? Okay. Shall I get started? Wonderful. Okay. So good afternoon, everyone. Today I'll be taking you through a journey on Blue AI, which is essentially talking about AI and data and equations that cover the physics of ocean. Yeah. Which cover the topics of ocean health and coastal resilience. So I don't know if in the room I cannot see the room unfortunately, but I would like to ask you if anyone in the room has ever seen this picture. Do you know what it means? I want to see the picture. Okay, I'll give you a bit of an explanation on what the picture is. This picture shows the average temperature of our planet Earth over the last century. So on the left is 1870, on the right is 2023. Blue colors are cooler colors, red colors are warmer colors. So this picture actually shows you, actually proves to you that our planet is getting warmer and warmer. So I'll ask you another question. Now you've seen the top picture. Do you know what the bottom picture means? I can maybe give you a bit of an answer already. The top picture, like I told you, is the warming planet. The bottom picture from 1970 to 2018, it shows the number of species of biodiversity in our planet. So on the left, you see bright green colors, which are a very biodiverse planet. And on the right, you see that indeed, because of the warming planet, our biodiversity on our planet is also decreasing. It is very much correlated. And 80% of biodiversity is actually in our oceans. So we see a lot of wildlife around us on land. In the water, in the oceans, it's much more biodiverse. And because our oceans are warming up as well, we are losing biodiversity. So essentially, climate change and declining biodiversity are very much linked. How do we measure this? How do we monitor this? We do this if we understand our oceans, if we have data about our oceans. And that's what I will focus on in today's presentation. So 50% of the degraded ecosystems are only over the last century in the context of the oceans. 80% of Earth's life, like I said, lives in these ocean ecosystems. The annual value provided by these ecosystems each year is about $2.5 trillion. So we're talking about a very vibrant ocean economy that depends on fishing, that depends on resources from the ocean, that depends on livelihoods on the coastal zone. And that's 4 billion dependent people on the planet. So half the world's population is relying on ocean for primary income or as a source of food. So that's how important the oceans are to us. However, we don't know a lot about our oceans. More than 75% of the world's ocean is unmapped, unobserved, and unexplored. We actually know more about the moon, we know more about Mars than we know about our own oceans. So that's the situation we are in today. My company, it's not my company, of course, it's the company that I work in. Sorry about that interruption. The company that I work for is called Fugro. Fugro is a company where we collect data from all kinds of possible platforms, all kinds of possible sensors, for the objective of creating a safe and livable world. Our motto is better data enables better decisions. We are able to provide decision makers who need to make decisions about coastal resilience, about ocean health. If we're able to give them quantified insights using data, then they're able to make better decisions. And what do these insights look like? These insights are mapping the baseline. What does the world look like today? Modeling risks. What are risks that are being faced by different kinds of assets, different kinds of infrastructure, different kinds of actually people? And then monitoring that over time.
Electrical
How
and
will the risk
Electronics
look like
Engineering,
tomorrow? What
SRM
will a
Institute of
coastline look
Science
like
and
tomorrow?
Technology.
If there's
It
a
is
certain
my
climate
great pleasure
scenario,
to introduce
what will
our
the world look
distinguished
like
speaker
in
for
10
today's
years?
session.
That's
In
the
a
sort of
room
insights
full
that
of
we
bright
provide to a
minds and
variety of
kind
different
hearts, it
clients,
is
including
truly a
governments.
privilege to welcome someone who
So we do this through a fit for purpose combination of different kinds of technologies. So whether it is satellite sensors, airborne sensors, vessel-based sensors, sensors that are on the seabed, robots that go under the water, USVs, you name it. A whole combination of different technologies where we pick and choose the right technology depending on the budget available, depending on the costs, depending on the use cases. Sorry, was there a question? Sorry, I heard some noise. Never mind. Okay. So I would like to zoom in into a specific use case because I think this sort of a story is much better told if we can zoom into a very specific use case and illustrate what we're doing on an actual project. So I would like to take you into the world of seagrass. Now, seagrass, as the picture shows you, is essentially grass that grows on the seabed. And you might think, why is this important? Now, this is very, very important because it's an extremely good way of storing carbon. A lot of 90% of the excess carbon that we produce is actually absorbed by the ocean. And within the ocean, the seagrass forms a wonderful carbon sequestration mechanism. It's about 35 times better at carbon removal than rainforests. And the problem, though, that we see is that seagrass is disappearing because oceans are getting warmer. It's about 7% of the seagrass, approximately, we don't know because we've not mapped it properly, is disappearing from our planet. That's, if you put it in perspective, about 1 football field of seagrass every 30 minutes. So that's how quickly we are losing seagrass. Not only does it sequester carbon, seagrass also provides food and habitat for a lot of marine, so fish and all this marine biodiversity. And 20% of the world's fish stock actually relies on seagrass. In addition, as a co-benefit, seagrass also protects coastlines. So it protects coastlines from erosion, it buffers the waves and storms, which actually has a beneficial effect on coastal communities. So it's a very, very valuable ecosystem in the ocean. However, we don't even know where seagrass is. 80% of the world's seagrass is actually unmapped. Where we do know there is seagrass, we have no idea whether the seagrass is healthy or not. Is it dying? We don't know. So what we're aiming to do is actually map the seagrass across the world. I did a bit of research on where seagrass is actually in India. There is quite a lot of work that's been done on the topic of seagrass in India. The map shows you some locations of where seagrass is located off the coast of India. They estimate about 517 square kilometers of seagrass coverage with the sequestration value of about 435 tons per square kilometer per year. So that's quite significant. In other parts of the world as well, there's a lot of seagrass, and I would like to take you through an example of a project we're actually doing in Italy, where we are mapping and monitoring the seasons, monitoring the changes over time, identifying areas where seagrass is alive, it's dead. This helps us also understanding the environment. It helps in detecting threats to really see which are the areas that are critical, where there's specifically pollution happening, etc., to conserve this sort of seagrass, but also guide restoration efforts to sort of look at where are areas where we can plant new seagrasses and make sure that this is a healthy ecosystem again. And all of this data helps in supporting policy and management. So the example in Italy, it's quite an interesting example because it's really the first of its kind in the world, which we hope to replicate in various other countries going forward. This is called the Marine Ecosystem Restoration Project. It is a project that is funded by the European Union. And the objective is to really restore and protect the seagrass ecosystems, focusing on biodiversity conservation and sustainable resource use. It aims to complete the mapping of the entire coastline of Italy by July 2026. And we only started the project this year. So we actually want to map the whole coastline of Italy in 2 years. Just as information, you probably have seen the map of Italy. You see that on this slide. The actual length of coastline that we're looking at is about 7,600 kilometers. So it's a huge amount of coastline that we want to map. And I'll give you a bit of a glimpse of how we're going to actually do this. So the concept of operation is follows. First of all, we are doing a large area coverage using satellite Earth observation. Through very cutting-edge technology that we are using, including AI-enabled analytics, we are able to look at bathymetric information as well as seafloor classification, the visible depth of the satellite. We're complementing that with airborne LiDAR bathymetry over the entire area. And this is very high resolution bathymetry data, as well as habitat mapping, which goes to up to 3 times the visible depth of the satellite coverage. So which means we're actually extending how far the satellites are able to see. As third level, we are using surface vessels and multi-beam echo sounders to extend that coverage even further from the coastline. And then we are actually doing ground truthing using AUVs to provide very high resolution RGB and hyperspectral imagery to feed the AI algorithms, train the algorithms, and also to see the algorithm. So using this multi-phase approach, we're able to provide information all through the coastline, but even at the resolution of individual leads. And I'll show you a few examples of what that data actually looks like. So like I said, we have all of these different layers of data, and as you can imagine, this is an enormous amount of data. We're talking ginormous petabytes of data. All of this needs to be put together, they need to be aligned, they need to be co-registered, they all need to be visualized, displayed in a coherent way. So that's we do analytics, and we use a lot of AI in the process because otherwise we cannot get the project done by 2026. And all of this is displayed in our platform that's called Fugro Vergeo. So Vergeo is essentially a cloud-based system. It has to be the cloud because, again, it's a huge amount of data. And by doing some very smart analytics, we're able to very quickly show insights about seagrass and itself to the Italian government through this platform. So a few examples of the different components that go into this system. The first is satellite Earth observation. So like I said, we capture satellite imagery over the whole area, and very quickly we can do classification to show, well, here is dense seagrass from one species, here is sparse seagrass from another species, etc. That is very quickly done using satellite data. The products there are seafloor reflectance, bathymetry, and a preliminary classification of the seafloor. Here's an example. Here's the data as it comes from the satellite imagery, and then we do the processing that gives us the bathymetric information, and then the first pass information of different habitat classes using satellite imagery. So in this case, it's seagrass, shallow sand, coral reefs, all kinds of things that are shown as a preliminary classification. Now, Here's another example of how we can really quantify some of the insights. So this is an example quite close by to Italy in France, where by using satellite Earth observation, we show that from 2023 in different months, so this is May, this is July, and this is October, we see what is the variation of seagrass cover even across these different months. So we're able to measure the above ground biomass of the seagrass very quickly using satellite imagery. And we can extend that over a multi-year program. So this is 2022, 2023, 2024. You see what the coverage is and you see what the biomass cover actually is and how it's changing over time. We do the same thing. We can do even more detailed analytics. We can look at seagrass density as well through a similar kind of processing. It shows the different patterns at long time. The beauty of using satellite data is we not only look forward, but we also look back in time. So we have access to satellite data from as far back as 1984, which means that we can also do historic analysis of data to see how has seagrass evolved over the last 40, 50 years to really start making these trend analysis and predictions about the future. So we complement satellite Earth observation, like I mentioned before, with airborne LiDAR bathymetry. And what does that actually mean? We use small aircraft, or we could even use a large drone if needed, and we have a very specialized sensor called the RAMS, the Rapid Airborne Multi-Beam Mapping System, which is our in-house innovation. This can be mounted on a plane or a drone, and it gives you a lot of these different end products from bathymetry, seaflow reflectance, seaflow classification, but also imagery, both RGB and in this case, we're also collecting hyperspectral imagery from the plane. This technology actually gives hydrographic information and hydrographic IHO standard accuracy. So very accurate hydrographic data along with water column information, which in the future we could use to study different kinds of things in the water column, whether it's biodiversity or any other thing that we want to study in the pelagic flow. So that's what we do with LiDAR. And of course, because it's a huge amount of point cloud data that's generated every single day, flight, we have to use machine learning to be very quick with data processing, cleaning up the data, but also producing the insights that we need about the person. So here's again a great example of machine learning in action. And then the last technology, or the last couple of technologies I quickly talked through, of course, everybody knows what MDES is, multi-beam echo sounding, which we have installed on several vessels that belong to Fugro. With this, we get bathymetry, backscatter, and seafloor classification information, and you get maps about the deeper waters through these sort of acoustic methods to complement the other technologies. So here's an example of data that's been collected in the project. And then, of course, we have tied it all together, and we need to, of course, make sure that we are able to do the classification in the correct way, which means we need to do ground truthing. And for ground truthing, what we use is an AUV, and the products that we collect are orthophotos and videos. And this sort of information, as you can see in this picture, you see the kind of resolution at which we're collecting seagrass information. So we start with a very broad scale and zoom in until we get this level of information about seagrass. And you can clearly see in this picture, you're able to classify where the seagrass is healthy, which is in green, where you see the seagrass not healthy anymore, which is the brown and the white seagrass. So this helps us really fine-tune our classification algorithms, our AI analytics, to make a very comprehensive map of the entire country. But it's more than just ground truthing. There's a lot more additional data we're actually collecting that we can use for a variety of different purposes. Additional products that we are providing are orthophoto mosaics, but also seagrass health estimates. Here's a great example of healthy seagrass, as you see the nice green pictures, versus unhealthy seagrass, as you see in these other pictures. So that is being used in addition to all of this other information, carbon stock, biomass, all sorts of information that we're throwing together with this big AI engine to be able to produce these very accurate maps. So here's a bit of an example of how we're doing the classification. The input data is like what you see in this picture. We do a segmentation. Obviously, when there are more features, a segmentation is more dense, and otherwise it's more sparse. And then we do training, and then we come up with, as you picture on the right, where we do a classification, and we come up with an output where it's hard bottom, where it's Estonia, and where it's sand, for instance. And this we are applying with it. Reverse magnetic speed, like I said, 7,600 kilometers. So not only do we do this sort of extent mapping, we're able to, of course, find out, okay, that is the extent of seagrass. Then we are finding out where is it healthy, where is it not healthy. And by doing analytics, we see, okay, there's a reason why over this area there is unhealthy seagrass. So we can do some analysis to see what is causing it. So for instance, we can start doing stressor identification. In this particular case, there was probably a factory over here that was leaking out pollutants. By doing some sort of modeling, we can understand where exactly is the source of the pollution that is causing the seagrass to die out. And this really helps the government to make planning, to really get to the cause of the problem as to why the seagrass is dying out. Even more is possible with Blue AI. This is really only the tip of the iceberg as to what's possible with Blue AI. So I'll take you through another example of a project we're doing in the Netherlands, but it's equally applicable really anywhere else, of where we are actually mapping biodiversity using machine learning. So we have technologies by which we can take underwater imagery and automatically classify them into any kind of life form that there is. So whether it's a crab or whether it is something else, some sort of a marine life form, flora that's growing there, that's identified very quickly, even if the ROV is struggling in the water in real time. So this epibentic species identification using machine learning is very much an area of research at the moment, and we are applying this on our project to do this inventory of biodiversity in these environments. So that was really one example. Of course, the same methodology can be used on any kind of ecosystem in the coastal zone, whether it's mangroves or whether it is, in the context of India, like what Sundarbans or anywhere else. We can really look at any kind of coastal life ecosystem and put together this data. Data by itself doesn't mean anything. Data is only useful if it can actually help solve someone's problems. So even though we have data gaps in the ocean, we talked about the fact that 35% of the ocean we know nothing about. The fact is we are generating a lot of data about our planet every single day, whether it's from satellites or whether it's from boats. By using Blue AI in the right way, in a responsible way, we're able to convert these huge amounts of data into really the small amount of crucial information that stakeholders need to be able to make decisions to solve problems. It's a bit like this Lego example that I often show with my kids as well. Data is like a pile of Lego that's just lying on the ground. You're stamping on it, hurting your foot when you're walking through the living room. At some point, you sort it. Okay, so you want to scope it, you start doing things, and then you want to maybe arrange it. You do statistics on your data, etc., etc. You get some information. For a lot of stakeholders, presenting it in a visually appealing way is very important. So you need to present it in a nice platform, in a nice web application potentially. When you start explaining it with a story and then finally making it actionable or useful, that's when it really matters, and that's when stakeholders can really take benefit from it. So hopefully we can use this sort of an approach even more in the future, and really make a difference to our planet using the data that we are generating. Thank you.
Questions?
Thank you, ma'am. Thank you for the wonderful session. Kindly accept this e-memento, ma'am.
Oh, thank you so much. Can you send it to me by email? I would love to have it.
Sure, ma'am. Sure.
Thank you. Thank you. Good.
I call upon Dr. Funny sir to introduce the session chairs.
Thank you, one and all, for your long patience in waiting. In this conference, I feel I take the privilege in calling upon our next session chairs. We have two session chairs, Dr. Paramita Chakrabarti and Dr. V. Sri Devaki Madam. So, Madam, first of all, on behalf of the organizing committee, I welcome you to this conference. Introducing Dr. Paramita Chakrabarti. She is a professor and is a top most cited researcher and is the head and is also the head of the Department for Center for Research in Environment, Sustainability Advocacy and Climate Change in SRM Institute of Science and Technology. Her research domain include multimedia transport of legacy and new persistent organic pollutants, the bioavailability of organic containments, environmental chemistry, transformation and remediation of endocrine disruption compounds and other emerging contaminants. So, Professor Chakrabarti has worked extensively on many Indian riverine ecosystems, including the transboundary rivers of Ganga and Brahmaputra. She is a big proponent of wastewater-based epidemiology for disease outbreak preparedness and has successfully completed several projects on developing an early warning system for SARS-CoV-2. Dr. Chakrabarti have numerous international and national funding. If you take, for instance, Research Council of Norway, the Norwegian Embassy, and the Swiss Agency for Development and Cooperation, as well as scientific wings of various departments of science and technology, Government of India. She has guided already six PhD students, and currently six students are pursuing PhD under her. She has over 108 international journal publications till date, published several book chapters, and Dr. Chakrabarti has also edited three books by Springer and elsewhere. She is a proud recipient of prestigious honors, including the Ajmal Khan Award 2024, ACS Early Career Chemist Award, Eminent Young Scientist for the year 2015. So, thank you, madam. Thank you for your time being here. I welcome you to the conference and I request you to take this as a chair for this session. Thank you, madam. And I also take immense pleasure in introducing another session chair, Dr. B. Sri Revati from Vellore Institute of Technology, Chennai campus. So currently, Professor Sri Revati is working at VIT Chennai from May 2012 to the current date. She has also been associated with SRM University with 5 years of experience here. She completed her PhD in Family of High Gain, High Power DC-DC Converter Analysis, Design and Implementation from VIT University. She pursued her Masters in Power Electronics and Drives and Bachelor's degree from Anna University and Periyar University respectively. So her research specializations include power electronic converters, renewable energy, machine learning applications for various electrical engineering domains. She has published 25 journals in high reputed and standard journals, published four patents and having four book chapters. So with warm welcome, we are also welcome you as the session chair for this particular session in our conference. Welcome you, madam. And I also request you head over the session from you. So I now request all the participants, all the authors of the paper IDs that I have shared. I request the authors to kindly occupy the space on my right side. So the first paper ID number 68. Paper ID 68. Yeah. I welcome the authors for paper ID 68. You can start your presentation. A brief instruction to the authors. Kindly make your presentation precise for 5 minutes. Thank you for your cooperation.
Good evening, everyone. I am Lucky Gupta, and this is Ayush Kumar from the Department of Computing Technologies at SRM Institute of Science and Technology. Today, we'll be presenting our paper titled as AI-driven multimodal frameworks for predicting and managing ocean deoxygenation. Okay. So, ocean deoxygenation is basically an alarming reduction in the marine oxygen levels that causes to the creation of dead zones, which basically cause a threat to marine biodiversity and overall ecological impacts. Our work is dedicated to developing an advanced early warning system which uses AI to efficiently and reliably predict ocean hypoxic regions. Talking about previous studies that are done in this work, they are majorly relied on in situ sampling observations that cause multiple major causes of problems. And earlier AI models that were used were CNN and LSTM. These models provided adequate results but were inefficient in spatial and temporal coverages. And they also faced inefficiency in data consistency and in class imbalances. In contrast, our approach uses CNN for extracting the spatial features, conv for temporal and spatial features, and integrating it in the end with ensemble model for the XT boost model. So, by integrating all of these in our ensemble model, we lead to mitigating all the previous problems faced by the earlier models. That is, improving the accuracy that is faced and the spatial temporal coverages that are needed. Talking about the major workflow of our model is that we first took various data sets that were present in WOA 2023 website, that is World Ocean Atlas 2023. The various data sets had attributes like salinity, temperature, latitude, longitude, depth, oxygen levels, etc. And we are proud to inform you that we have successfully published our data settlementally data so that we maintain a transparency and provide further researchers to work with it. Then we found the oxygen level, that is hypoxic region level, through some calculations and standard WO 2023 websites, which shows that any region with low oxygen level below 62.5 mu mole per kg is considered as hypoxic, whereas above that are considered as non-hypoxic.
Hello everyone. As you can see our proposed methodology here, our framework is built upon three models where spatial analysis is via CNN. Here, the CNN model is tasked with extracting spatial patterns, from features such as geographic coordinates, depth, salinity, and temperature. This step enables precise identification of regions that may be at risk. Secondly, spatiotemporal modeling with conv Here, the conv captures the variance of oxygen levels over a period of time, enhancing our capability to monitor evolving hypoxic conditions. Finally, the ensemble integration. Here, to leverage the strengths of different modeling paradigms, And to counteract the class imbalance between the non-hypoxic and hypoxic areas, we have integrated predictions from the CNN, Cornwell STM, and XGBoost using a logistic regression meta-learner. The XGBoost model was used for its robustness to handle imbalanced dataset. The logistic regression meta-learner then effectively combines the outputs from the three models to deliver reliable detection of hypoxic regions by reducing the model's overall complexity. Uh, Here, we moving on to the results. Our evaluation concentrates on the task of detecting hypoxic regions. The ensemble model demonstrated performance, or remarkable performance with an overall accuracy of 98.7% and more importantly, a recall of 0.99 for the hypoxic class. This detection rate is vital as false negatives in the hypoxic region identification could have serious ecological consequences and waste of resources. Uh, Moving on to slide 8. In conclusion, our result establishes a AI-driven framework that effectively predicts and monitors ocean deoxygenation by finding hypoxic regions with high accuracy. By combining the strengths of CNN, Cornwell SPM, uh, and XGBoost in an ensemble model, we have developed a tool that can serve as an early warning system, which is mainly needed for marine conservation and suitable resource management. There are also multiple future scopes for future research. Integration of multimodal data, such as implementing in situ sensors and nutrient information that can further increase the predictive accuracy. Thank you for your
Anush, nice presentation. So can you tell me which, reef in the ocean, the data you have taken from?
Ma'am, the data set WOA, World Ocean Atlas 2023, this has the global ocean data.
So it's the overall global ocean
Yes,
data.
yes.
And have you checked with some of the ground truth data, like
Uh,
real time? This is the model
Yeah,
data.
yes, ma'am. The data in the data set, the oxygen values, everything is from sensor.
And like it's like there can be seasonal data. There can be is it just a one time data? You have a time frame for this?
Annual year wise.
It's an annual data, averaged out data. Okay. And what kind of environmental applications you think you can utilize with this model?
Ma'am, from this, we can recognize by early warning system, we can recognize areas which can fall, like, the oxygen level can fall to the critical thresholds, and then we can apply some remedies or like cross measures to fix that in that area, like, increasing nutrient values or any other methods that can overcome the hypoxic threshold, increase the
I think
oxygen
you
level.
did a wonderful job, but just a suggestion next time, just to specify a region. It's better because around the year the values may not be the same.
Yes,
Yeah, and so it can be specific. If
Yeah,
you're writing,
working on that currently right now, ma'am.
great. Thank you.
Thank you, ma'am.
So, what are the modalities that were integrated in your framework, like satellite data, on-site sensors? What are the modalities you have?
The major data which we have taken is through NASA satellite or Sentinel data, and as well as we have taken in situ sampling data through the sensors. So yeah, that's it.
Okay. And how did you address this synchronization and resolution mismatches?
Okay, so we are using XG boost model, which causes which is effective in table formatted data, which leads to higher accuracy. So that let us suppose so the levels of hypoxic regions to be present and not to be present are very unratio. So for that we have used SMOTE, that is a technique to balance the classes so that the accuracy is better and such that the regions with low probability can also be measured accordingly.
Okay, how will your model distinguish between natural variabilities and man-made pollutions in ocean deoxygenation?
So we are, if we extend the model to different parameters, we are taking nutrient levels and we take it further. Like we have considered the basic levels right now, like the temperature, salinity level of the water and the oxygen levels. But if we take it further, like the oxygen levels can also tell about the nutrients level, like nutrients present, which can be like altered due to the pollution levels as you told. So that can be done further. But yeah, we are taking the basic values right now.
Like maps and we should have the scalability considerations so that the model can be deployed for different coastal regions.
Sure.
And how is the uncertainty quantified in your prediction model? How will you quantify the uncertainty?
For the edge devices, like the one that will be deployed on the coastal regions, they would have to have been like lighter models that we will have to create. Like this is an ensemble model, so like it uses CNN, Conval STM and XGBoost. So these are like a little complex models. So like the meta learner that we have used is logistic regression. So that is to reduce the overall model's complexity. So the meta learner enables us to decrease the overall complexity of the model, so that it reduces the time for training and then for predicting the results.
Yeah. Discuss more about
We are open to any suggestions that you gave. It would be really nice for us to work further.
just the 10 minutes presentation. I cannot give any give this point. How do you want it? And so can you the that can be for other type of early warning systems can be noted from some other early warning.
Okay, so considering other parameters also, yes, we can do that. But currently, it is just for like ocean levels, the hypoxia region levels. But yeah, it can be integrated further to other storms. Thank you so much. Thank you all.
Thank you, others. Next, I call upon paper ID 95, Kavya to get people.
Good evening, all. My name is Kavya from ICRCFT. Today, I'm going to talk on the topic deciphering environmental drivers of the jellyfish bloom dynamics in the northwest coast of India, a citizen science and remote sensing approach towards the coastal management. So, as you know, jellyfishes, they are gelatinous zooplanktons which are present worldwide, and the rising of the jellyfish blooms and swarms is a rising concern nowadays. So, coming to India, our study focuses on the Gujarat part, where we can see seasonal fisheries of the jellyfish is also there. But many parts of the Gujarat, there are other jellyfishes which are non-edible jellyfishes which are causing so much problem for the economic, ecological, and so many problems with the fisheries also. So the jellyfishes are very highly unpredictable and they have very negative impact also. So and there are so many studies are coming for the jellyfishes, but majority of the studies are focused on the fisheries of the jellyfishes. And now here we are going to do the environmental variabilities, that what are the parameters that influence the jellyfish's bloom. So and further we are already into the project and we are focusing on the creating an advisory for the jellyfish blooms. So monitoring of the jellyfish is a very expensive and challenging task, and so we are using the citizen science thing. So
So our aim is to unravel the environmental drivers of the jellyfish blooms in the northwest coast of India. So these are the study areas where you can see the locations of the jellyfishes, and these are the sampling locations where considered as the jellyfish hotspots. So coming to the data methodology to quantify the objectives, we have used the citizen science data. That is, we have asked the trawlers or the fishermen of in the Veravel coast, that is in the Gujarat, to collect, to send us the photos of the jellyfish if they are getting in the trawlers. So they have uploaded, we have created a WhatsApp group with 21 fishermen, and they will be uploading the photos of the jellyfishes when they are getting. And we consider that as the season one, that month where they are uploading the jellyfish photos as season 2, and season 1 as the jellyfishes where they haven't there is no photos of the jellyfish uploaded. We consider this as season 1. So it is from the span is from January 2023 to 2025. So after identifying these, where they will be also uploading the locations, GPS also, so we can identify the jellyfish hotspots. From that, that hotspots will be taking the remote sensing data like environmental, like SST, salinity, SSH, nutrients, etc. We are taking it, and we have a comparison of the environmental parameters between the blooms and the non-bloom periods we have taken. Then what we have done is we have gone through the exploratory data analysis. From that, we have plotted the box plots. Correlation analysis was done. Correlation, from the correlation, so many variables were like correlated. So we done the principal analysis, component analysis. GAM modeling was done. GAM modeling is a generalized additive model. Then from that, we were able to identify the jellyfish location. So these are the box plot we have identified. From this, we can this is the season 1 and season 2. Season 2 is a season 2 is a jellyfish blooming months between January 23 to January 25. And season 1 is where no jellyfish blooms was observed. So from SST, salinity, and chlorophyll, there is a moderate differences in the jellyfishes, and only in the post weight we can see there is no much significance. Balance all the like sea surface current, SSH, and eastward flowing, we can see that there is much differences. So what we have done is then we have gone for this GAM modeling. Now coming to the generalized additive model GAM modeling, so we can see the SSTs. You can consider this SST. So in SST we can see the dotted lines we can see, that is the predictive, and the solid line where you see it is the this is the actual value, and you can see the horizontal line which says the range of the SST, and the vertical line which says what is the SST, that is what association of the SST which have with the catch data. So we can see that in first SST about 25, it is like moderate. Optimum SST is about 25, and likewise we can see in the salinity also there is a moderate and seen from 33 to 35. Now likewise chlorophyll also is seen, and it is also moderate, and SSH we can see silicate, nitrate, and phosphate. Phosphate there is no much significance, and it is so not at all a significant thing we can say. And so coming to the conclusion, we can use the GAM modeling for it is a strong fit to the catch explaining the large proportion of the variance. We can use the GAM modeling to identify, to correlate, to extend the conducive conditions of the jellyfishes, and so the environmental factors like SST, salinity, chlorophyll, etc. We can see the optimum temperature, salinity, silicate, nitrate, and sea surface current also using the GAM model prediction. So this is how we are going to do, and in future what we have to do, planning is the AIML integration precision also will be done for this jellyfish advisory. So this is about my project, and these are my references used and acknowledgement. I thank Director ICSEFT and SO Info Hyderabad. Thank you. Thank you, ma'am.
We collected data.
Ma'am, we are, even though we are collecting the data, we are using in situ data also. We are going like fortnight sampling we'll be doing. For modeling, for citizen science modeling, we need more data is needed so that the extended time period increases, and we'll be contacting more other fishermen also to come into the to upload their photos. Likewise, we have to do.
So, what are the key entered variables that influence your results?
So environmental variables will like salinity, temperature, sea surface temperature, salinity, sea water current, then in nutrients, silicate and nitrate influences.
And how do you rank them in terms of
GAM we have done because after we have correlated, we have gone for the principal analysis correlation. Then after that, we have done the we have gone for uh, histoplots we have done. So in the histoplots, it was like non-linearity was there. So GAM generalized active model is a very good tool for the non-linearity to represent. So we have gone for this GAM.
Like we tell you the rank in terms of importance.
Sorry, ma'am, I didn't know.
You have got so many key environmental variables that are affecting your results.
Yes, ma'am.
But how do you rank them in terms of importance?
Ma'am, we are finding out the conducive conditions for the jellyfishes. So we can identify like if in the GAN model we have run the all the parameters, and we have understood also the what is the right range of the salinity that jellyfish blooms can appear. They may like in the future also at what range, if the salinity is there, if the temperature is there, at what range the blooms can again go. So this is how we have found it, ma'am.
Okay, how do you address the seasonality in case of events like cyclones, etc.? Does your model address them?
Seasonality in the model, seasonality become a parameter also. So, yes, ma'am.
So does it? Or do you consider some normal events like cyclones, etc.?
Till now, no, we don't know. Thank you.
Yeah, Kavya, yes, bringing in citizen science for prediction is a very good idea. I mean, very rarely in India we are doing, you're trying to incorporating citizen science, very good. But citizen science also brings in a lot of uncertainty. So, what I see in your box plot, your SST between the seasons are not varying much. So, how do you explain the jellyfish blooms? Like, what I feel is like, do you consider the amount of data the fishermen are giving you is actually really correlating with the seasonality? Because, if you look into the box plot, I see the median values. The two are not varying much in the two seasons. Wherein in your write-up, it is there that there is an impact of sea surface temperature. And you also mentioned that, but I don't see much variation in the median value in the box plot. So how do you explain that? Just that one question.
Sea surface temperature, it is in the moderate, ma'am. Like we can say sea surface temperature from like 34 and 35, we can consider it as, 25 and 26, we can consider it as a moderate sea surface temperature. So, but we cannot apply on only one parameter. So if you are taking the case of jellyfishes, not only one parameter can do. Like all the parameters come into the effect. Like we cannot say like if sea surface temperature increases, bloom appears or jellyfish increases. We cannot say like that. All the parameters have to come into effect. So this is how we are moving towards the environmental variabilities coming into the model and putting like to provide the advisory, we are doing like that, ma'am.
So, what do you think? Can you list two parameters which are impacting the blooms? The prime parameters among the ones that you have done, or is it there is a requirement of considering more water quality?
One of the prime parameters we can see is the sea surface current velocity we can take. Why is that so? Because we are like fortnight, we are also sampling, we are taking the samples, so going for the sampling also. So in the model also, it had a prominent place for the sea surface current.
Also, when we interact with the fishermen, they also they will be also more focusing on when we be asking like what is the reason, like what is we will be preparing questionnaires for the fishermen also. So from because they will be having more experience than us also. So from their opinion also we are getting into conclusion that sea surface current is one of the reason for the jellyfish, because jellyfish doesn't have that much like a moving capacity. It moves with the current, and because of this current, what happen is that the jellyfishes have sexual and asexual mode of reproduction. So, in the sexual mode of reproduction, they will be in sorry, the sexual mode of reproduction, they will be attaching that polyps will be attaching to the like corals or rocks. And Gujarat is a part where there are so many rocks are available, like corals and rocks are available. So, this current is also the reason for the jellyfish to bring the jellyfishes their larvae to settle down, and then from that they will be going. So, I think sea surface current is one of the biggest factor that contribute to the jellyfish bloom.
Thank you. Thank you.
Thank you, ma'am.
Okay. Next, I call upon paper ID 159, AI-driven plastic waste detection in ocean for a sustainable future.
Project is based on AI for predicting the plastic deposit in ocean. So it's already a known project. The thing we choose this is enhancement of the accuracy and precision because all the parameters which have been produced by other research papers. So our first interest, I need to come from the black side so that you can know the inside of it. So the major thing we made this project is a comparison table we took from recent papers from 2024, 2023 and 2024 second paper, and all these are the models. Yes, so these are the models which are taken from the papers, and this is the proposed work is the R model. So if you see the accuracy and the precision with recall, R's are matched with other quality. So this is the observation we got from it. For the first paper, you can see the precision is not that accurate. So there is less false positive, and comparatively there is no better F1 score in the second paper when compared to ours. So all these data have been calculated and we compared to this. And the basic thing of doing this is we used simple CNN model with 4 layers. We didn't complicate anything. The time it takes for training was bit confusing because we used many models first. We used many AI models, image processing models to get this result. And finally, we got this because our filter was in increasing order 6, 16, 64, and again decreasing to narrow down the output of these values. So, 1 minute. I'll go back to the architecture side. Yeah. So this is the thing. So we narrowed down because after processing each pixels in the image, we'll get an encoding values. So we need to again narrow down to have two results, either plastic ocean water or non-plastic ocean water. That means this is the image we used. So that's the plastic. Can you see there, ma'am? This is a clean water compared with plastic deposited water. And this was the train. Like I have 4 pictures because 2 is from the training data set and 2 is from the testing data set. So the total split up was around 90 is to 10. Image used was 2180. In that 8880 is for plastic and 840 is for non-plastic in training data set, and 220 is for non-plastic and 240 is for plastic. So totally 2180 data sets have been used. And first thing is all images was not taken by myself. It was given at the Kaggle, which was published by Cornell University from an ocean data set. So that data set was clearly randomized because each data has a different alignment. One was in horizontal, one was in yellowish fade because the image was degraded. Because the image data was not collected at the same spot, it was collected from the previous year, it seems, and the image data were not accurate. But the Cornell University have justified that these data have been truly collected from these ocean waters. So when seeing the images, we have a bit confusion. So we have data argumentation, the next process after completing the data collection. So in the data argumentation, we first resized
the image to focus only on the plastic and the water surroundings, because you see that there are many empty areas there. So I just want to cover this plastic first. If there is no plastic, I don't need to resize. So I've reduced the size from 2240 cross 2240 pixel. I mean, the width in red. Second thing is the data augmentation. The second part is I have even reduced the width for 10%. From the 2240 to 2240, reduced for 10% to like localize the plastic image. And then I told the image was in cross order, color orientation. Some images were zoomed out. Can you see the plastic in that map? So you can't see the plastic in that, but that image has some plastic. So I need to zoom in. I have a percentage of zoom in of 20% so that it may be have some plastic in it. So to do it, I have also added zooming percentage in that. So these are the things I have done in data augmentation. That next goes to the label encoding. As usual, to name the plastics, we have 1 and 2, and that 1 and 2 is like transmitted into binary values using encoding, one hot encoding. So next is building the architecture. So this was quite interesting thing. I told you before, it was an increasing order of filters. I mean, kernel size. So from 6, 16, 64 and 32. The reason is 6, 16 was increasing my accuracy and 64 was paring my accuracy. Next, to narrow down the perfect accuracy with this, I need to reduce the kernel size to 32. So I use ReLU for this. And next, the output of each thing is next given to the dropout layer of 0.5%. The reason of dropout layer is I got overfitting in my training data set. So I used dropout to minimize the overfitting things. Finally, a dense layer was used with 128 features. So this is the model which I built for predicting the image in the ocean. And now this is the result I have got. Overall result, I have mentioned different results for each, plastic separately, non-plastic separately, so that it will be a bit more accuracy and a trustable work done by done by the previous work from other papers. Because when I see these papers, these are work for combining all plastic, non-plastic, and empty images. They don't have any split option with how much of accuracy in plastic, how much of accuracy in non-plastic. So I have then this like splitting out, and my conclusion is best balance of precision, recall, and F1 when compared to the other models. So, based on the future scope, it is really useful to implement in drones to detect plastic because it's cost effective. Right now, sea plastics are collected using ships or any sea workers go inside, scuba divers, many used to go inside. It's cost effective and it's like really unpredictable sometimes. You can't go in depth also. If you fix this in any electronic devices or like drones, AOV vehicles or underground water vehicles, this is really useful for them to predict, and it is cost effective and safer for humans also. Though it is malfunctioning, that's second part, but it's really safer. Safety because humans are not disturbed in this. Next thing is we can even implement this in sky drivers also, like who come around sea values to check whether any plastics or deposits are there. Like seaplanes, some things will go for detecting the unusual metrics inside the sea. So you can even merge this type of camera with them. So this is the future scope I have found from it and some stuff given my professor. Yeah, and it's great privilege. And these are the papers which I have taken from. You can see the years I have mentioned. So all were from recent years actually, because this is already a known project. Many of you have done this. So to make it enhance, I need many papers from latest. I mean, recently published papers. So I have chosen many from 2024, 23 years. And thank you, ma'am.
Thank you, Rohan. Very, very important topic and it's of prime interest to me as well.
Thank you.
YOLO software, like, YOLO was used like quite some time.
Yes.
Initial YOLO versions were not that great.
Yes, ma'am.
So, can you combine YOLO with CNN or
No, basic CM. Basic CM. Yeah, but I've complicated the architecture of it. Like I've used filter of 3x3 for first one, 5x5, 5x. I told 4 layers, 3x3, 5x5, 5x5, and again 3x. So that filter size and the kernel of filter size has reduced. I told to narrow down the output result. We need only two binary output, whether it is plastic detected or not plastic detected. So I've varied the filters of.
Now tell me one thing, like when you are binary, okay, so plastics are basically polymers, synthetic polymers, and if we see any living organism inside, any living organism, that is an organic polymer. So many times it's actually challenging to identify this polymers. In general, we have to use very high-end machinery, even for the very small plastics, which are maybe mesoscale or microscale. But my question is like with this binary, one is your color, right? But what if you are confused with the color?
No, I'm not changing the color format. I'm just like and you're asking about the encoding system, right?
Yes.
Yeah, encoding system is to identify the image number. If it is plastic number one, plastic number two, plastic number three, plastic number four, non-plastic number one, two, three, for like processing the like camera processing, it takes some time. To make it faster, I have just encoded the numbering sequence into binary so that to calculate sequence. I'm not changing the color of the images.
That's what.
So image of the color is same. No. Image of the color is same. I'm not changing them.
But it's a very good,
Sure.
of course, this
Sure.
needs a lot of iterations, but a very good job. I really
Sure.
appreciate it. I really like your presentation. Thank you.
So, data sets are taken for training detection model like satellites from
No,
drones
ma'am.
and
All are from seawater, underwater, underwater. These are taken from Cornell University.
so there is no data sets from satellites that is not
No, ma'am, they didn't have any data set from. They had images of 2180, which are all from their university published links. So that maybe I can improvise with satellite data also. But it has top layer waters.
So, if you want to use it for real-time thing, marine systems, or like marine groups, marine voice, etc. What are the latency and deployment requirements?
Yeah. Right now, I used with my computer laptop camera itself. So, like, I just took a print of a photo which is in the training set. So, it was not that late to find it. I didn't have the estimate time for whether it takes this much of time to predict whether it's plastic or non-plastic. But yeah, it was quite easy to predict. It was not taking a laggy time sequence. But it takes complicated when we exactly deploy in an hardware. Yeah, it takes some time, maybe. But I didn't move into hardware part yet.
Look into the cost benefit of deploying such AI systems in the coastal monitoring.
Yes, I feel like this doesn't cost that much because I'm going to implement this in already previously existing models. Like already there'll be a drone for monitoring sea activities, or there'll be already a UAV systems that is for sea activities, underground submarines for sea activities, just a camera which around costs some dollars. That's it.
So you can do some cost analysis.
See, ma'am, it's like just a coding part, having to federate it to a controller or any processor. So I don't find much cost for this. Because I'm going to like this is only going to fix on the previously existing model. This is just an AI model going to fix the previously existing hardware. I'm not going to build a new hardware for this.
Right. So if your framework can it be extended to classify macroplastics and microplastics?
I didn't test on that side because I didn't have a data set for it. Once we get the data set, I can even try for it. But I guess it's not so because the layers which I've used are old. CNN is like far old now. Many new models now. Well, wait, 10 is going to come. So the accuracy of Ola model will be really lesser than comparative to new model. The thing of using CNN is still CNN is standard. So you can even predict normal. Like predicting anything using CNN is still standard and that is really a coursework. So I use CNN for normalizing the effort. Though I could have used Euro V9 also, but I find CNN is a bit easier to do than YOLO V8 because YOLO V8 is more generalized purpose. You can use for anything. You don't need to train. This is already pre-trained. This is you need to train your image data set. I find you have a positive approach when you have your pre-trained model than using a someone's trained model. Thank you. Sure.
But no, you're using approach model of what Ram is telling me that is if you want to go for a smaller particle size, then nowadays like Intel is coming up incorporating higher imaging in the camera. So that helps a lot, to understand the particle size. So what the approach is good, very good, but it needs a little bit of more enhancement. Yeah. So incorporating a lot of new things into the picture. the bigger part of science make it works. Like, there is a French group we're working with where the painting, painting will have some amount of plastics or even microplastics in the marine world. And this is not other organisms, but including their cellulism. So that is also quality. So to distinguish that, I is a must. So the particle science changes, but your approach with the way you have to what's very good.
Maybe I can test with diaphragm because
Yeah.
for us it can differentiate plastics and so it will be a bit more accuracy also.
But it's in that case, accuracy.
Yes, because plastics. Yeah, plastic has a different higher observation skills. Yeah, each has different higher observation skills. So I could have tried that probably.
But very good. That's easy how you try that.
Thank you.
Next presentation is from paper ID 124, Linear Static Analysis of Fixed Offshore Jacket Platform.
Myself Joshua from Chennai. I currently pursuing a master's degree in naval architecture offshore engineering at Ahmed University, Kanatu. And this is my first paper conference I'm attending. This is my topic related to ocean engineering, linear static analysis of fixed offshore jacket platform. And I'm going to fix this install the platform in the Kaveri Basin at the water depth of 80 meter. And aim of my analysis is to check the unity check ranges because I'm going to install this platform. So I'm going to check the unity check ranges. And by using the all the API codes, by using the numerical tools, I'm going to ensure that my jacket platform is safety or not. The numerical tools which I'm going to use here is SAC software. So it is an analysis software related to the offshore structures. And the introduction of the platform is first the plate girder and the tubular welder frame supported with by the welder frame. It's called the jacket platform. And the range of the jacket platform will be up to exceed up to 500 meter only. They are not exceed up to it should not exceed up to 500 meter. Why? Because the jacket platform will be installed in the shallow waters only. So if they are exceeding up to 500 meters, it will be go for another platform like complaint towers and so many platforms there. So but the fixed jacket platform they will be installing only below the 500 meter only. So this is the literature survey I have taken for my platform. First, Grandison there 2018, the analysis of the jacket platform in the Mumbai basin. She did that for the 79 meter depth, and another one is relativity of four length jacket platform. And these two literature survey I taken for mine. I have taken the reference for my platform. This is a jacket offshore platform. The jacket offshore platform will be considering two types. Like they will be separating two things. Like here you can see that top side they will separate, and this is the bottom side. From the seawater level to the sea mid level, it's a jacket structure. Total of this height is 80 meter, and this will be separated. Top side structure will be separated, and the total height will be taken as 103 meters. So in this top side structures, there will be taking as cellar deck and main deck. In cellar deck, there will be machineries and other equipments, and in main deck, accommodations, helipad, and other related to the production related of oil and gases. Everything will be taken place here. And these are the types of the water depth ranges. As I said, like in the jacket and GPS means gravity based structure, and jack of brick is 0 to 500 meters only, and these are the ranges where they are taking for the platforms. And this is the methodology. The first stage in the four stages I'm going to do it. First, I'm going to create a model by using the numerical tool, and I'm going to give the properties and the load out weight features and combining all the load out combinations. And after that, I'm going to give an analysis. In that analysis, I'm going to give a three analysis. First, the pre-analysis model and the post-analysis and the post-view database. I'm going to check it. Once if I get that post-view database correct only, then I can proceed that my jacket platform is ensure in the safety condition. If I got any post-view database wrong, then wrong means any error, then I have to recheck my model. And the final stage is the first stage of analysis is linear static analysis. There are so many analysis like ballast analysis, collapse analysis, damage, so many analysis there. The first stage they are checking the linear static analysis for the checking of the ensuring the jacket structure is safety or not. In that linear static analysis, they will checking the after if they get jacket structure safe condition means they will go for the unity check ranges and the moment diagrams also. So this is the block diagram I have taken for this. First I create a model, as I said, first I create a model and the load of combination analysis and the pre-process, post and the performance of linear static analysis. And the code criteria. Some of the code criteria I am going to give giving in the for the jacket platform. These are there are so many code criteria. As I said in the introduction part, by using the API codes only, we are going to create a model. So these are the code criteria API and RP. To API means American Petroleum Institute and RP means recommended planning. And these are the codes they are using for the offshore jacket platforms. So for my jacket platform, I taken this one WSD means working stress design and AIS is steel construction. For all the jacket platform, they will be considering as the steel only. So AIS means American Institute of Steel Construction. And the 14th edition RP2A 21st edition I have chosen for this. So this process only we are going to be I am giving in that analysis step. So this is a linear static analysis. What is the linear static analysis means? It's a in place analysis, also called as in place analysis. Why we are evaluating this means? Sorry. So the structure how responds to the loads. So we are checking for the structure property. They are checking the linear static analysis, and this linear static analysis is used to determine stresses, displacement, and the reactions taking place in the jacket platform. These are the boundary conditions I am giving for the platform. So seabed flexibility. These are the 7 steps I give it. These color codes will be the presetting layer. If the green color means it is a safe condition. Yellow color means it is a limit condition only, reaching to the limit, but it's a safe condition. And the red color denotes it's a failure condition. Well, once if I got a failure condition, then I have to recheck my model. So after giving the performance, after giving the analysis, I got this total structure of my it's a yellow color. Then I got for it's a related to the safe conditions. In the top deck, you can see that it's a red color. Why? Because I didn't give any loads in that. So it's showing a red color. So only thing I have to recheck this part alone. So in this future course, I'm going to check it this read part and I'm going to check all this whether it's a green color, green stage condition or I'm going to check it. So once I check it, I predict that it's a performance of the linear static analysis by using the numerical tools. I predict that it's a performance of linear static analysis. So these are the analysis that have taken place. First, I created a model and I give the member properties and using the loader combinations combining the analysis. And the final stage is the performance of the linear static analysis. And after giving the performance of linear static analysis, this is the graph I got it from the numerical tool. And this part of 104 to 204 is affected by more static loads. And the range, maximum range I got it 0.54. So it should be below 1. If my range came below 1 means, then I can say that my performance